Tango Charlie to Pat, coming over.
Pat, this is Tango Charlie, go ahead.
This is just to inform you that the Vanna is now going to leave with Pat crew is not necessary anymore. Over.
All right, copy that.
In the meantime, we are at step Bravo 6-10. We have removed all the RBS from the rocket. Over.
Copy that, you have removed all the RBS from the rocket.
And we are now going to proceed to raising the tower. Over.
Copy that, please proceed.
Then one last thing, Tango Charlie, could you maybe already get cursor ready for us to measure the elevation? Over.
Copy that, I will inform Falcon to contact Corso. Over.
All right, perfect. Pat out.
All stations, this is Tango Charlie. I'd like to inform you that a few seconds ago, the high altitude weather balloon has been released 5 minutes ahead of schedule.
Via Bravo, this is Via Alpha, please come in.
This is Via Bravo, go ahead.
We're plugging in the load cell, so stand by for measurements. Over.
Copy that, standing by.
The load cell is plugged in.
Copy that. Could you please move to another channel? Over.
And now?
Pat, this is Tango Charlie, please come in.
This is Pat listening. Over.
We've requested Corso to come to the pad. He will be there in about 10 minutes. Over.
All right, seems good to us. Over.
Tango Charlie out.
Via Bravo to Via Alpha, come in.
This is Via Alpha, go ahead.
Just to inform everybody, the load cell seems to be in working order. Current reading mass is around 4 kilograms. Over.
Via Bravo, to please read the elevation while the rocket's going up. Over.
Copy that. 20 degrees.
Please continuously speak every 10 degrees, over.
30 degrees. $40. 50. 60. 65. 70. 73.5 degrees. Current measured angle is 78.2 degrees, over.
Via Bravo, this is via Alpha.
This is via Bravo, go ahead.
Could you please give us a load cell indication, over?
Current compensated load cell value is 161 kilograms, over.
Let's go, thank you very much.
Copy that. Current angle is 78.8 according to my measurements, over.
Yeah, we'll get Corso here to validate the angle.
Roger that, over now.
Tango Cherry to Pat coming over.
Pat, this is Tango Charlie. Go ahead.
Can you check the view from camera 4 and tell us if you're also happy with it? On the pad, we are happy with it, but let us know what mission control thinks. Over.
All right. Camera 4 is of the filling arm. Let me see. There was someone standing in front, but he moved now. Please stand by.
Correction, Tango Charlie. I mean, camera 5, the one from the bottom of the rocket. Over.
Copy that. Looking at camera 5. Again, please stand by. All right, Pat, to confirm, we are happy with the view. We have a clear overview of the umbilical as well as the retraction system itself. Over.
Yes, copy that. We have the same opinion. We're quite happy with it, so we'll keep it fixed now and won't touch it anymore. Over. Tango Charlie 2 Pat coming over.
Pat, this is Tango Charlie, go ahead.
This is to announce that the tower erection is complete. Over.
Copy that. Tower erection complete.
So we have also measured the elevation, and we have an elevation of 78 degrees. That is 78.0 degrees. Over.
Copy that. 78 degrees elevation. Over.
Also, as a reminder, the azimuth geographic was 201.5 degrees. Over.
Copy that. Geometric 201.5, making magnetic 202.5. Over.
We're then moving to step Bravo 6-22, and we're going to confirm the views from the different cameras. Over.
All right, copy that. Please proceed.
So we should have a view of the upper skirt thrusters openings, the bleed valve, and PRV exhausts.
Copy that. We can see that on camera 2, 3, and 4.
You should have the engine nozzle, although that is the view that is now pointing down. Looking down from the upper umbilical. Over.
Copy that. Indeed, the nozzle is not fully in view of camera 5. However, camera 2 suffices for safety purposes. Over.
Copy that. You should also have a view from the upper umbilical and URS from the top. Over.
Copy that. That's cameras 3 and 5.
You should also have a view from the disconnects and lower umbilical and the ground feed system and dump line. Over.
I can confirm we have a view of the quick disconnect and lower umbilical. Please stand by for ground feed system and dump line. We are reaching out to Papa Sierra. Please stand by.
Tango Charlie, can you repeat? Over.
We are reaching out to Papa Sierra. Please stand by.
We have a question.
Pat, this is Tango Charlie. Please come in.
This is Pat listening. Over.
I've discussed the situation with Papa Sierra, and we both agree that the current camera views are sufficient for safety purposes. Over.
Okay, copy that. Please note that the camera pointing towards the quick disconnects will be moved forward at the end of Charlie. Over.
Copy that. I was expecting that. Over.
Vio Bravo to Pat, coming over.
This is Vio Bravo, go ahead.
Can you give me the current measurement from the load cell? Over.
Stand by. The load cell is currently reading about 160.5 kilograms. Over.
All right, copy that. Over.
Via Bravo, this is via Alpha, please come in.
This is Vio Bravo, go ahead.
Could you please check date of the Rio? Over.
The current state of the Rio is armed. Over.
Okay, thank you. Out. Via Bravo, this is via Alpha, please come in.
This is Vio Bravo, go ahead.
Would you please enable the power on the lower umbilical? Over.
Enabling the power on the lower umbilical. Stand by. Enabling power on lower umbilical in 3. Power enabled.
Could you please let us know as soon as you get connection with the ECU? Over.
Confirm I have connection with the ECU. Over.
Would you please enable the upper umbilical? Over.
Enabling the upper umbilical in 3. Upper umbilical is enabled.
Could you please relay us when all boards are connected? Over.
Confirm all boards are connected. Over.
Tango Charlie to Pat, coming over.
Pat, this is Tango Charlie, go ahead.
This is to announce that the lower and upper umbilical are connected to the rocket and that we are at the end of checklist Bravo. Over.
Copy that. We are at the end of checklist Bravo, 55 minutes ahead of schedule. Do you confirm? Over.
I confirm. Over.
All right, that's great news. I will do some com checkouts, and after that, I suggest you get started on checklist Charlie. Over.
Okay, copy. Can we request to take a very short break for us to quickly go up and down to the bunker, grab something, and then be ready to continue? Over.
Of course, no problem. Go ahead. Over.
All right, copy that. In the meantime, we're also going to send away Shendo and Elvin with Timo in the Mocha. Over.
Yeah, sounds good to me. Over.
All right, perfect. I'll let you know when we start Charlie, and in the meantime, Bad out. Over.
So that, just a heads up. I see him walking with his phone on the webcam. Over.
Yeah, thanks. I anticipated on that. I see they just arrived, so I'll check again in a minute. Over.
Tango Charlie, this is Pad listening over.
But this is Tango Charlie. Could you please send Roderick to the Cocolos channel? Over.
Yep, copy that, will do. Over.
Pat, this is Fire Bravo. Please come in.
This is Pat listening, over.
Timo is wondering if it's safe to approach the pad right now. Over.
Yes, it is. He can approach, over.
Okay, I'll send him over. Out. Yeah, it's Pat, this is Vio. Please come in.
This is Pat listening, over.
We are wondering about the status of checklist Charlie in case we have to make launch now or later. Over.
We're getting ready and we're going to start in a few minutes. Just getting everybody ready on the pad, over.
Okay, then we'll just grab a drink and I'll be right back. Over.
Copy that, over. Tango Charlie 2 coming, over.
Pat, this is Tango Charlie. Go ahead.
This is to inform you that we are ready to start checklist Charlie, over.
Copy that. Go ahead. Starting checklist Charlie. In the meantime, could you give me an update on the quick disconnect?
There was some small fixes, and I was already sending Timon to check if it was good while we were just waiting here. But I think it is pretty good. Over.
All right, copy that. We'll follow progress. Over.
All right, pad out. Vio Bravo 2 coming over.
This is Via Bravo, go ahead.
Can you confirm that both umbilicals are powering the rocket? Over.
Please stand by. I can confirm both umbilicals are powering the rocket. However, we would like to do a quick power cycle of the upper umbilical. Over.
Okay, go ahead. Over.
Copy that. Power cycling. Alright, we can confirm both umbilicals are powering the rocket. Ready to proceed. Over.
All right. That. Can you also confirm that all the internal systems show up launch interface? Over.
I can confirm all internal systems are visible on the launch interface. Over.
All right. Copy that. Over. VO Bravo 2 coming over.
Miss 5 Bravo, go ahead.
We are ready to perform an actuation checkout of the valves. Are you ready? Over.
Copy that. Stand by for 1 second. Ready on my side. On your mark. Over.
Can you open and then close the ground fill valve? Over.
Opening and then closing the ground fill valve. Opening in 3. Closing in 3. Valve actuation successful.
Yeah, the actuation was successful. Over. All right, VO Bravo. Can you open and then close the dump valve? Over.
Opening and closing the dump valve. Opening in 3. Closing in 3. Opened and closed. Over.
All right, VO Bravo. Can you open and then close the main valve? Over.
Yes, I'll first enable the battery for the main valve. Over.
All right, go for it. Over.
Opening the main valve in 3. Main valve opened.
You can close the main valve. Over.
Closing the main valve in 3. Main valve closed.
All right, we confirm the good action of the main valve. Now moving on to the tank valve. Open and close the tank valve. Over.
Copy that. I'll first disable the batteries and then I will proceed to the tank valve. Over.
Okay, copy that. Just let me know. Over.
Alright, ready to activate the tank valve. On your mark.
You can open and then close the tank valve. Over.
Opening and then closing the tank valve. Opening in 3. Closing the tank valve in 3. Tank valve opened and closed. Over.
Okay, confirm the good actuation of.
This is via off at the pad. Please come in.
By listening, over.
Martijn is wondering if it's safe to approach with Nirvana. Over.
Safe to approach.
Okay, I'll tell him. He's coming over right now. Oh.
Via Bravo, can you actuate the valve?
Actuating the bleed valve, closing first, closing in 3. Bleed valve closed. Opening in 3. Bleed valve opened.
All right, we would like to do it again with the bleed valve. Can you close it and then open it again? Over.
Please say again. Over.
Can you once again close and then open the bleed valve? Over.
Copy that. Closing and then opening the bleed valve. First closing in 3. Closed. Opening in 3. Opened.
Okay, copy. With a good actuation of the bleed valve. Moving on to the clockwise roll control valve. Can you open and close the valve? Over.
Copy that. Proceeding to the clockwise roll control valve, opening and then shortly after closing. Opening the clockwise roll control valve in 3. Closing in 3. Closed.
All right. Can you do the counterclockwise roll control valve? Can you open it and then close it? Over.
Copy that. Opening and then shortly after closing the counterclockwise roll control valve. First opening in 3. Closing in 3. Opened and closed. Over.
All right. We confirm the good actuation of the valves. Over.
Pat, this is via Alpha. Please come in.
Come in. Over.
We were wondering if it's possible to do one more checkout of the main valve.
All right. Copy that. Can do the main valve. Over.
Okay. We'll open it, wait on your confirmation, and then close it again. And then again, wait for your confirmation. Over.
Copy that. You can open the main valve. Over.
Yeah. Ready to open the main valve. Opening in 3.
Confirm it is open. You can close it. Over.
Closing the main valve in 3.
I confirm it is closed. Over.
Copy that. Stand by, please.
Okay, Pat, you're clear to proceed. Thank you. Out.
Tango Cherry to Pat coming over.
Pat, this is Tango Charlie. Go ahead.
So this is just to inform you of the situation. The filling arm needs some minor adjustments again, but it might take a few minutes. So in the meantime, we suggest to move already to testing the heating lamps. Over.
Copy that. Minor issues with the filling arm. Moving on to the next step before returning back to testing the filling arm. Over.
Yes, exactly. We will return to the quick disconnects whenever possible. Over. VO Alpha to Pat coming over.
This is via Alpha. Go ahead.
2, 1, 0.
propulsion of the Stratos IV rocket.
Sponsorship Acquisitions Manager.
The Joint Chief Electronics with the other Jasper. So I'm the Chief Electronics. Electronics Engineer.
I will continue with my treasurer responsibilities.
Chief of the Structures Department.
I'm what we call the Process Manager.
Chief Recovery of the Stratos IV.
Part of the recovery team, the lead engineer on the roll control system.
Head of Food Logistics. I'm the Team Manager.
Chief Engineer. So what I didn't expect was how intense and exciting it would be.
Blood, sweat and tears.
Cherry on the tip of the iceberg, yes.
People working days and nights, every week, every day.
Seeing this launch is just going to make everything so worth it.
It's now the full circle.
And I'm already smiling when I think of it.
It's just so cool. I love it.
Fourth pair enabled, over.
Alright, I confirm the good actuation of all the heating lamps. You can now turn them off, over.
Copy that. Turning off all heating lamps one by one, starting with number 1, over. All heating lamps are disabled, over.
VO Alpha to Pat, coming over.
This is VO Alpha, go ahead.
We would like to already move over to step Charlie 1-49, the pressure sensor readings, over.
Okay, go ahead.
Can you give me the current reading from the tank pressure sensor, over?
Please stand by. Yes, tank pressure sensor is currently 0.81 bar.
Alright, copy that. Can you give me the pressure reading from the combustion chamber, over?
The combustion chamber is currently
Can you repeat? You said 8.0, over.
sorry, all the way around 0.8.
Alright, that sounds better. Thank you, over.
Okay, thank you. Out.
VO Alpha to Pat coming over.
This is VO Alpha, go ahead.
We're gonna start again with the test from the filling arm. So at step Charlie 1-29 over.
Okay, please stand by while I get ready. Okay, ready on your mark.
VO Alpha, can you open the quick disconnect? Oh,
Opening the quick disconnect in 3, 2.
can you close the quick disconnect? Over.
Closing the quick disconnect in 3, 2.
Okay, VO Alpha, you can open the quick disconnect. Over.
Opening the quick disconnect in 3, 2.
You can close the quick disconnect. Over.
Closing the quick disconnect in 3, 2.
Alright, VO Alpha, that was the first successful test. We're now going to do it a few times again. Over.
Okay, standing by.
You can open the quick disconnect. Over.
Opening the quick disconnect in 3, 2, 1.
You can close the quick disconnect. Over.
Closing the quick disconnect in 3, 2, 1.
You can open the quick disconnect. Over.
Opening the quick disconnect in 3, 2, 1.
You can close the quick disconnect. Over.
Closing the quick disconnect in 3, 2, 1.
You can open the quick disconnect. Over.
Opening the quick disconnect in 3, 2, 1.
You can close the quick disconnect. Over.
Closing the quick disconnect in 3, 2, 1.
You can open the quick disconnect. Over.
Opening the quick disconnect in 3, 2, 1.
You can close the quick disconnect. Over.
Closing the quick disconnect in 3, 2, 1.
You can open the quick disconnect over.
Opening the quick disconnect in 3, 2, 1.
All right, I confirm that we have 5 good actuations of the filling arm. Over.
Copy that. Good job, guys.
You can close the quick disconnect over.
Closing quick disconnect in 3, 2, 1.
Two, 1, 0.
COVID. The main issue with COVID was that we lost a lot of our production facilities. This meant that in the midst of a pandemic, we needed to search for new places and sometimes even methods to make sure that all our parts got produced. In the end, however, we managed to pull through with some support of some of our sponsors so that we could produce everything in time for the launch.
All the buildings we work in, they shut down. That was pretty problematic as a lot of my work is practical. Mixing the fuel with raw ingredients, you have to be there with 4 people. It's not something you can just do by yourself. That was a big issue for us. However, what we did, we all went home and we started working on all the documentations, all the computations that still had to be done, such that when we could actually access the buildings again, none of the paperwork had to be done anymore. We could just focus on all that practical stuff.
Compared to some other departments in the team, you know, like the structures department, which needs a lab to work in, I could argue that we were one of the lesser affected aspects of the Stratos IV team, as a lot of the things we could do, we could still meet online very easily, we could still make social media posts, we could still communicate with sponsors. although our edge, as you might call it, or our ability to do so was severely impacted.
So yeah, COVID was quite tricky, especially with the big lockdowns. Yeah, labs closed up, and our electronics stuff we need is in the labs, and not all students have a fully fledged workspace at home. So electronics progress stagnated. A lot of the physical stuff we couldn't do. We could write some code, but we could only test it in a limited sense. So it just came down to like documentation and code and that kind of stuff, but not really the PCBs or any of the electronic components. This last summer, everything was open up again. We could really, yeah, get the work and finish it. So that was really nice.
So I think it's impacted it on two fronts. First of all, being generally the team, how did we run? How did we run with our team? How did we work? How could we even access the rocket to build it? So that was a really big challenge, and it was mostly we had to think really creatively, as in, okay, where at any place can we do these certain things for the rocket? So where can we work on our electronics? Where can we actually access machines to still produce certain parts? Where can we get composite material for the rocket? Because now we didn't have one centralized workspace anymore that we could access, so we had to do it all over the place. But still, while doing that, make sure that everything afterwards would fit together, and that was also done safely and not like randomly, and not that things got lost. And then also, how do you do your meetings and all of that stuff. That was one big challenge. So not only just working from home, but also working in little workplaces, basically. That was one challenge, that we just overcame by being creative. And then the other one was, we're going on a big campaign with a lot of people. So at max we're about 36 people. That's quite a large group. So how do you do that safely? Because normally you want everybody to be healthy and you want them to be safe when you're launching a rocket. But now you want them to be extra healthy because there's now an additional risk added into the formula. So for that, that was quite a tough one to figure. Okay, how can you still make the project work as best as we can, so that everything on the rocket side and the technical side is still done successfully and safely, but also that the people themselves remain healthy. So we took some inspiration from events such as the Olympic Games, Formula 1 races, big events, and then tried to translate that into what we needed.
Alright, VO Alpha. I would like you to perform a mock-up fire counting from T minus 15 seconds until T equals 0, and read out loud the time over.
So just to clarify, I'm pressing the button from 15, I'm counting down from 15 to 0, holding the button at 10, releasing at 0. Is that correct? Over.
That is correct. Over.
Okay, then I'll arm Gabriel, and ready on your mark.
Can you check the tower? Over.
Tower selected is right tower. Over.
Okay, copy that. You can go for the mock-up fire. Over.
Okay, mock-up fire in 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Gabriel, safe.
Alright, VO Alpha. We confirm that it was a success on our side.
Perfect, nice to hear.
VO Alpha, we're going to save Lucifer on our side. Can you also save Gabriel on your side? Over.
Yeah, Gabriel's safe.
Lucifer is on safe. Over. VO Alpha to Pat coming over.
This is VO Alpha, go ahead.
Can you give me the reading of the load cell over?
The load cell, do you want it angle compensated? Over.
Sure, over.
The angle compensated load cell reading is 167.72. Over.
Copy that. We're going to add a mass of 8 kilograms to it. Over.
Okay, then we should expect an angle compensated mass, so a little bit less than 8 kilograms. Over.
What is the current reading? Over.
1.72.3 kilograms. Over.
All right, we are removing the mass. What is the current reading now? Over.
168.3 kilograms. Over.
All right, copy that. Over.
Pat, this is Tango Charlie. Please come in.
This is Pat listening. Over.
The values we saw here were different than Vio called out. Could you please repeat the test with Vio and see what the reason might be? Over.
Will do. Over. Zero Alpha to Pat coming in.
This is VO Alpha, go ahead.
Can you give me the current reading of load cell? Over.
Current reading of the load cell is 168.55. Over.
Okay, we are now going to attach a known mass of it. Over. Should be 8 kilograms. Over. What is the current reading? Over.
Still stabilizing. 173.15 kilograms. Over.
Copy that. Over.
1, pull.
Today we're standing at the open jet facility of the TU Delft. This is a wind tunnel that can go up to 30 meters a second and in which we test different parachutes for dare. The different types of parachutes we've tested today, or which we focused on over the last few days, are the Disca band parachute and the Hemistflow ribbon brogue parachute.
DP, you can start the tunnel. Turning up the wind tunnel to 25 meters a second. 5, 4, 3, 2, 1, pull.
After the unfortunate breakup of Stratos III, Delft Aerospace Rocket Engineering did not give up and started project Stratos IV, which is, as the name suggests, the fourth iteration of the Stratos mission. The goal this time is not just to break the European amateur altitude record, but to go to space, to break the 100-kilometer line and make DARE the first student team to achieve this feat. We as the Parachute Research Group support the project by developing the recovery system that will bring down the flight data safely. One of the parachutes behind me, the Disca band, is the main parachute of Stratos IV, and the other parachute is the drogue parachute, which is the Hemistflow drogue parachute, identical to one that flew on Stratos III.
The Hemistflow drogue ribbon parachute is a special parachute that can go up to high Mach numbers, and this is used in a lot of Stratos missions to retrieve the nose cone safely. It is also being tested for its high Mach capabilities on the supersonic parachute experiment aboard Rexus. This is a mission that will fly on the Rexus 28 sounding rocket in March 2020. The drogue parachute is made out of 150 different pieces of tape. So you can imagine it takes a little while to produce this thing. Currently we've got it down to about a week of production time.
So behind me is the actual test bench that we use to deploy and measure the performance of the parachute. As you can see, it's quite a sturdy design made out of steel to make sure that it doesn't bend and doesn't go anywhere during the tests. We have a 3D printed white canister on top that we can use to safely store the parachute and deploy it on command. But most important is the load cell where the parachute is attached to. That load cell feeds into the laptop so we can measure the drag generated by the parachute during the deployment and during the static behavior.
So today we've tested the Disca band parachutes, a Disca band clustering and the Hemistflow ribbon drogue parachutes under varying conditions. But in our next wind tunnel test campaign in May, we will also test the sequencing of these parachutes together in a Stratos and Spear configuration.
I've come to Pat. Could you put me in contact with PR? Over. VO Alpha to Pat coming over.
This is VO Alpha, go ahead.
Can you please listen to your Porto? Over.
Okay, Porto, stand by.
Welcome everyone. We had the opportunity to join the launch campaign of the Stratos IV rocket, where Sebastian is working on the recovery section of the rocket. He had a couple of minutes time to give us an idea of what the entry, descent and landing system of the Stratos rocket looks like. Welcome Sebastian, great to have you here. Could you give us an introduction of who you are and what Project Stratos is?
Yeah, so thanks for inviting me, Thomas. So my name is Sebastian Oliver Scholz. I'm currently the Chief Recovery of the Stratos IV project and a master's student at TU Delft. The Project Stratos is a project that started about 3 years ago, where we want to build a rocket fully done by students to reach and break the European altitude record, the student altitude record actually. And yeah, we want to do that by building a hybrid engine rocket.
All very impressive.
Yeah.
So how does the recovery system specifically of the Stratos IV rocket work?
Yeah, so we use quite a few different systems for recovery. We first want to ensure that all of the internals of the recovery bay and the nose cone stay intact. So we use a heat shield to pretty much protect the internals during re-entry, during the heating phase. Then we deploy a drogue parachute. So we use a Hemosflow ribbon parachute for the drogue parachute. And then afterwards we deploy a main parachute after it's stabilized. And then this will pretty much slow the capsule down to about 70 kilometers per hour and it will touch down in the sea.
Oh, great. So what kind of materials will we be using for the parachutes?
For the drogue parachute, we'll be using mostly aramid-based materials. So we use Triron for the canopy of the parachute, and we use Technora for the suspension lines and rudder lines. And then for the main parachute, we use mostly F111 nylon fabric for the canopy, and we use Spectra suspension lines, and also some nylon for the riser as well.
Good. All very high-strength materials, especially
Yes.
for the drogue.
Yes.
So you mentioned the drogue parachute, that it will slow down the capsule to velocities where the main parachute can be deployed.
Yeah.
But will you be deploying the drogue parachute at supersonic conditions?
For our case, no. The Hemosflow ribbon parachute that I mentioned that we use for the drogue parachute, it can be deployed supersonically. It has a very wide range of Mach numbers that it can operate in, also dynamic pressures. But we saw that during our simulations that the nose cone is quite unstable during descent, and it will enter a flat spin, so it'll tumble. This will also bleed the velocity down a lot, which we saw that it would be more beneficial to deploy the drogue parachute subsonically, so at a much lower height. This will avoid certain flow phenomena that occur during supersonic and even transonic regimes.
That makes sense. Why use the high-risk scenario where you can keep it safe?
Exactly.
That makes sense. So what kind of deployment devices do you use to deploy the drogue and the main parachute?
For the drogue parachute, we use a mortar system, which we call the hot gas deployment device. It produces a very hot gas using nitrocellulose and some black powder for the igniters. We have a certain plenum volume that allows the the drogue parachute to deploy around 18 meters per second. This allows the drogue parachute to be deployed without being entangled, as the capsule will be doing a flat spin. And then the main parachute will be deploying using a very simplified spring system. This is because the drogue parachute will stabilize the vehicle, and therefore it will not be going down in a flat spin. And therefore we just went with a very simple spring system just to deploy the main parachute around maybe a few meters per second, maybe 1 or 2 meters per second, and just to keep it simple.
Oh, that makes sense. Do you use sort of a pilot chute for either the drogue or the main parachute, or do you just rely on the deployment devices themselves?
For the drogue, we don't use any pilot chutes. We attach the lid that pops out of the canister to the parachute bag. This will ensure that the momentum of the lid will take the parachute out of its bag. But for the main parachute, we use a fairly big pilot chute just for to ensure that the main parachute really gets out of its bag, and that's that.
Oh, interesting, very interesting. So what kind of testing methods have you used throughout the years to prove that these parachutes work, or prove that these deployment devices work?
Yeah. So for the mortar, we did a lot of different tests. We first tested using a battleship canister. This was just to test the proof of concept and see if it was actually feasible. We had very successful tests with those. Also to measure the internal pressure and the ejection velocity that we get by varying the amount of nylon bolts that we use for the lid. And for the main parachute, we did a tabletop test deployment where we just removed the parachute out of its bag by pulling it out of the canister, and we've also just had the whole system assembled and then just cut the wires using a pair of scissors and seeing how well that would eject the main parachute. And so far those tests were all successful. And not only that for the deployment systems, but for the parachutes themselves, we validated them in the wind tunnel by assessing their stability performance at subsonic conditions.
Oh, great that you can use a wind tunnel.
Yeah.
Great resource.
Yeah.
So have you always used these types of parachutes for previous Stratos missions as well, or did they use different types of parachutes?
So for the previous Stratos mission, Stratos III, we used the same drug parachutes, it's the same Hemisphere ribbon design, same size and same shape, and we didn't see any need to change this design. But for the main parachute, we changed from a cross parachute for Stratos III to a disc gap band for Stratos IV. The biggest reasoning is because testing. The cross parachute is very unstable, and it was very hard to get any quantitative data from it. And we just saw that a disc gap band was a lot more stable, allows for a little bit better drag performance at a bit of a cost of volume, but we saw that was perfectly fine and we went for the disc gap band.
Great, yeah, the disc gap band is a beautiful parachute.
Yeah, it
completely
is.
agree on that point. So how do you plan to find the rocket nose cone back after it has landed safely in the ocean?
Yeah, so for our final phase during flight, we have the retrieval module. From our simulation data, we saw that we will be quite away from the coast, so the nose cone will land quite far away. And therefore we use an Iridium module. So this is the active retrieval system. The Iridium module will give us an approximate location of where the nose cone is. And then we will navigate with the boat to the area where we have the location data and start a search pattern. And meanwhile, once we're in the vicinity of where the nose cone has landed, we will then look out for the passive system that we use on the nose cone, which is 3 strobe lights. So these are 3 water activated lights, which is mainly useful for night retrieval. And we also have fluorescent dye in water soluble bags that will also help us to locate the nose cone.
Oh, great to hear that you have multiple options to find this nose cone back.
Yeah.
Quite an endeavor. As a final question, also for the viewers, when will you be launching the Stratos IV rocket?
Yeah, so yeah, that's a good question. We'll be launching around the middle of October, so it's coming up very soon. So make sure to keep up on their social media, on Facebook, Instagram, and LinkedIn, because we will be live streaming it, and we definitely hope to see you there.
Great to hear. It's great to see that you're all working so dedicated on this project.
Yeah.
We as Shoots will be following carefully along with your launch campaign, and we'll be excited to see the launch. Thank you for spending the time with us, and good luck during the coming weeks.
Thank you.
All stations, this is Tango Charlie. We are now proceeding at step 35 and we're going to continue with the FTS test.
Hello guys, so why don't we start off with a short introduction. Dion?
Yeah, I am Dion. I have been in DARE for I've been in DARE for 7 years. This is my 8th year. Yeah, I've studied aerospace engineering.
Okay. Rolf, what about you?
I'm Rolf. I am now in my 7th year at DARE. I'm studying aerospace engineering as well, as I suppose most of us here.
Okay. So, over the past 3 years, we've had this project Stratos IV. What have your guys' roles been in that?
In the start, I was a full-time propulsion engineer, which means I helped out with developing the main engine, as well as Stratos III forensic investigation, and that sort of culminated into my role as roll control propulsion engineer.
Yeah, for me personally, I haven't been as involved in Stratos IV as Rolf has. I was briefly involved at the start, but then left the team because I didn't have the time to spend on it, and then I kind of moved on towards more safety roles, and I was basically being safety officer for all the ladder tests that they did for the propulsion team, for example.
What does being a safety officer entail?
Right, so you can imagine that building rockets is kind of inherently very dangerous, and especially when you deal with stuff that's super high pressure or using pyrotechnics, you want someone there to make sure that people aren't doing anything stupid necessarily. So I'm just kind of there to oversee what people are doing, make sure that they're not doing anything dumb, and yeah.
So both of you guys are involved in the Stratos IV launch campaign, which is why you guys are in Spain. So what are your guys' roles in the launch campaign?
Yeah, so kind of a continuation of what I was doing for Stratos IV, not really being in the team, is that I will be the pad safety officer. So basically you can imagine that anything you do for an engine test, you're kind of hooking that all up to a rocket now, and you want to make sure that people that are doing stuff there, or doing stuff with flight termination systems and such, that the people there are doing it, but they're doing it in a safe way, and no one's going to get hurt accidentally or anything. So that's kind of what I do for Stratos IV.
I think that really runs in parallel with what I'm doing as well. I think the two of us are in general responsible for safety of this project. My role is flight director. It sort of originated from the Stratos III investigation as well, knowing how the anomaly went, being involved with the chief simulations to develop some of the software, where I was advising on implementing safety aspects into that simulation, and that in the end culminated into being the flight director, so together with INTA personnel ensuring safe execution of the flight of Stratos IV.
Okay, so both of you guys were part of the Stratos III launch campaign. So what were your roles for that?
During the Stratos III launch campaign, I joined and helped building up the Livestream. I wasn't involved in the Stratos III project necessarily. I worked on some of the smaller projects in there, gained my experience. And here was a lot of watch and learn, see how a launch campaign is executed, and see how things are done.
Yeah. I was also involved in the live stream, although before going to the launch campaign I was already heavily involved in the propulsion team, which is also why I helped out the Stratos IV propulsion team a little bit when they started out, and also more towards the end. So I was there doing some stuff on assembling the engine, that sort of stuff. And then later, when all that stuff was done, then we basically just had to put the engine on the rocket. I was hosting the live stream. So I worked a lot with Rolf then. He did all the technical stuff. I just had to look pretty and talk to the camera like I'm doing now. Hello. Yeah, so that's kind of what I did during the Stratos III launch campaign.
Okay, so Dion, since you were a bit more involved in Stratos III, what was the aim of that project?
So the aim of Stratos III was to kind of go as high as we possibly could with what we had available to us. We had a lot of lessons learned from Stratos II+, which was the rocket that we launched before, and we kind of wanted to see like what we could do like with the means we had to go as high as possible. We learned during Stratos II+ it's a bit silly to set a specific altitude goal, because if you don't reach it, you look a little bit silly. So we just said like we want to go as high as possible, and that's kind of what we did. Well, you know, kind of what we aimed for at least.
So I can imagine that you guys had a lot of problems during your project. What kind of problems did come up, and how did you overcome these during Stratos III?
I mean, yeah, we certainly did. I mean, I obviously was very much involved in the engine development, and boy did we develop that engine. We did so many tests in the end, and we had so many failures because these engines, we basically built the biggest engine at the time ever built by students. And the type of engine we use, a hybrid rocket engine, doesn't necessarily scale very well. So it was double the size of what we use for Stratos II+. Completely new engine, and it means that manufacturing becomes difficult. You now have to lift an engine that's 100 kilos instead of like 25, 30. Like, it becomes a lot more difficult in that sense. And that's just from a propulsion point of view. It's just very, very high level. If you look at the electronics have been completely redone. We didn't really work as much with composites before this. The tank is immense. It was basically the big size constraint on the rocket, and like just, you know, the thing that set how high and how far we could go. So that there was so many different things. Also flight termination systems, which had to be professional rather than us making some circuit board. We actually had to get it certified and such. So all of that was very, very challenging, and in the end we did overcome most of those challenges, and we eventually launched the rocket. So yeah.
So yeah, you guys launched the rocket. However, mid-flight a anomaly occurred. What was your guys' reaction to that?
Well, it was kind of a punch in the gut, to be honest.
Yep. Yeah, really.
Like, I mean, like, I had like some data streams open on my laptop as well, so there was no guesswork really involved to be like, okay, we lost the rocket. But man, it felt really bad. I mean, of course, for me, I was working on that rocket for two years or so already, and then all that work is just suddenly gone. And then the second thing I thought was, I hope whatever happened was not something that was directly my fault, because, you know, it's everyone that's worked on the project, and everyone's like kind of like, well, man, I'm not sure how to react to this. Like, I'm not sure what happened. No one knows what happened, and yeah.
Yeah, I remember when the rocket launched, the Livestream, we switched over to this optronics third view. So we looked in that case at the infrared footage of the rocket, and at some point there was this black blur around the rocket, these circles. I was like, oh, this does not look good. And then suddenly it was all in focus again. Turned out there was a lens switching. But basically 3 seconds after that initial relief, suddenly everything just stopped. You saw a bunch of black dots, and that was it. And then you realized this does not look good.
Yeah, plus everyone was absolutely exhausted because we launched this rocket at 3:30 in the morning, and at that point we had been heating for five and a half hours. And of course the entire day leading up to it. So everyone was really tired, and it was just really an awful feeling.
I think one thing that's really noteworthy though is that this team was able to launch the rocket at 3 o'clock at night.
Yeah.
It just shows the perseverance they had in order to push this through. There are some technical difficulties they had to overcome during that one launch attempt. And all the other launch windows that were open in the days after didn't have wind conditions that were favorable enough. So the fact that they managed to get that rocket to lift off on that one day is just an immense result.
So Rolf, earlier you mentioned that you were part of a forensic team that looked into what happened during the Stratos III anomaly. So what was your guys' thought process going into this investigation?
I suppose the first thought process was like, whoa, this system is complex, the problem is complex, the data is limited, how are we going to address this? We were with 6 engineers, mostly Stratos IV, which means we were continuing the project but not necessarily so involved in the Stratos III project. So there was a lot to learn about the rocket, about the vehicle, and just trying to tie all those theories together. All the theories that the experienced members had, the ideas of what could have gone wrong, and figuring that out was one of the largest challenges there. So after sorting out all the theories and ideas of what may have caused the failure of the rocket, we started collecting supporting and opposing evidence for all of those theories. Then some of them are rejected, otherwise stay open. And in the end, the one open one was inertial roll coupling of the rocket.
So another name for inertial roll coupling is also roll pitch coupling. What exactly is this phenomenon?
What it basically entails is that the rocket wants to spin at a certain rate, so it starts rolling on its axis, and then it stays at that rate, and it basically starts to make this cone motion. So the tip of the rocket starts to move around in circles, and that just becomes more and more excessive over time. And at one point, the aerodynamic forces become so large that the fins shear off and the rocket breaks up. Well, one large important factor in roll pitch coupling is the structure of the rocket, so the stiffness of the entire assembly. If the rocket starts bending, your thrust will not go straight through the center of the rocket, so as you can imagine, that helps pushing it to the side a little bit more. So that's one large factor, and there's other factors such as how symmetric the rocket is built, as well as slushing of the oxidizer.
And what was the method for preventing roll pitch coupling on the Stratos IV rocket?
So the method was twofold. One part was do as best as we can, but we can't quantify this, and the second one is we can quantify it and want to test it. The first one was improving the stiffness of the rocket and also improving the stability of the rocket. So you'll see the fins are a completely different shape as they were for Stratos III. The problem is that you can't quantify if that work is enough in order to battle this problem. Therefore we decided if you use a roll control system, it's a system you can test separately beforehand. You know how it performs, it's predictable, and that would make us more comfortable in knowing that this launch can be a success.
We can confirm we received only the carrier, and after 3 seconds, the failsafe terminate was enabled. Falcon, can you please transmit the FDR failsafe disabled tone combination? We confirm the FDR has turned up. Falcon, can you please stop transmitting the FDR failsafe disabled tone? Vio, this is Tango Charlie. Can you please switch on the FTR?
Switching on FDR in 3, 2, 1. FDR on.
Vio, we are now at step 77. Can you please switch off the video downlink?
Tango Charlie switching off video downlink in 3, 2, 1. Video downlink is off.
Vio, please switch off the FTR.
Switching off the FTR. FTR disabled.
Please confirm you're not receiving any data or video.
Confirmed, no video.
We are now at step 83 in the procedures. This is the end of substation checklist Charlie, and we have finished our FTS test successfully. We will now hold the countdown timer at T-minus 3 hours and 30 minutes.
Tango Charlie, this is Vio. Please come in.
Wow, this is Tango Charlie. Go ahead.
This is just to let you know that we seem to have regained connection with the telco station, and it looks like it's broadcasting video. However, locally, I don't receive anything. Might not. It might be something with the laptop that is reading the stream, but at least we're not receiving anything. Over.
All right, copy that. Shall I redirect you to VEE? Over.
Yeah, it's mainly a streaming issue, not a hardware-related one. Over.
All right, copy that.
Tango Cherry to Pat, coming over.
Pat, this is Tango Charlie. Go ahead.
Could you please tell me at which step we are at in the main procedures? Over.
We have currently finished step 83 in the main procedures. So we finished the FTS test successfully and are now holding the timer until the Rio has been flashed with the new software. Do you copy? Over.
Copy that. Over.
Tango Charlie, this is via Alpha. Please come in. Tango Charlie, this is via Alpha. Please come in. Tango Charlie, this is via Alpha. Please come in. Tango Charlie, this is via Alpha. Please come in. Tango Charlie, this is via
VO Alpha to Pat coming over.
This is via Alpha, please go ahead.
Can you please open the quick disconnect? Over.
Stand by. Okay, I'm ready. Opening at your command.
You can open the quick disconnect. Over.
Opening quick disconnect in 3, 2. Quick disconnect opened.
Nice. You can close the quick disconnect. Over.
Closing quick disconnect in 3, 2. Quick disconnect closed.
Okay, thank you. Pat out.
2, 1, 0.
Jasper, Jan, and Jillis, they're really nice.
2, 1, 0.
So I'm Jasper Jonk, I'm the Joint Chief Electronics of the Stratos IV. Together with Jasper, Jan and Jillis, we make the electronic system of the rocket. So yeah, first of all, the team, Jasper, Jan and Jillis, they're really nice, good company to work with. But especially what I like most about the electronics is sometimes something doesn't work for some obscure reason. And if you then figure out what it is and fix that problem, it like massive excitement to fixing it, and it just feels really good. And just seeing the rocket now with basically all the PCBs work together, doing the job, but still talking to each other, it's great. Good that you just light and it just shoots up. But it would be pretty boring if you do absolutely nothing, and from the time that you lift it off till it splashes down, it's just flight, nothing happens. If you want your rocket to do something, like gather some data about the flight or deploy some parachutes to recover it, you'll fairly quickly need some electronics, and that's where we come in.
The function of your electronic system and 3 main points.
So for 3 main points, the system is divided in 3 different sections. So you have the bottom section, which just opens the valves and takes care of the burn state. So is the rocket on, is it off, should the valve be opened or closed? Then in the middle you have the bleed valve controller, which is also houses the roll control system. So if the rocket spins too far to the left or too hard to the right, it tries to compensate. And then on the top you have the recovery and nose cone section, which houses the parachutes and all the sensors for recovery. So for electronics, yeah, we make our own PCBs. So we first draw up our initial schematics, saying, okay, we have a certain system has to do this. Try to break it down to small things, or as small as possible, and then we make a PCB design out of it, and we order it, we assemble it, and then we see does it actually do what it should do, or is the circuit wrong, or should we change some things. And usually it takes 2 revisions to get a fully working PCB. And in our rocket there are like 15 to 20 PCBs, so it takes a lengthy amount of time. Oh wow!
This is in the shot.
I was like, why are you watching? But,
keep going.
Really cool.
Okay, so you mentioned PCBs, I'm going to ask you what PCBs are, right?
Okay,
so that you can then edit it.
PCB stands for printed circuit board. So yeah, we make our circuits, and at some point we want to transfer them from the digital computer-aided design to the real world, and we basically give our circuit boards to a company, and they print them, kind of like paper, but then our circuits, such that we can work with them and actually assemble them. Yeah, so big companies with higher budgets, PCBs are relatively expensive to buy one and manufacture them, both time-wise and cost-wise. Big companies, they would just buy off-the-shelf stuff and just write code. However, yeah, we want to optimize for as much stuff as possible, and of course it's always fun to make your own things. So that's why we make all the PCBs in-house. We solder them ourselves, and we test them ourselves, and we write the code ourselves, so that we really have a product that's our own, but in the end it takes way more time to develop. For our development, our electronics relies on a lot of input from other teams, which a lot of the input, a lot of the information was only known later on in the process. So, for example, for recovery, they need to open the chutes, but the sequence on how they open it is undefined. So that led to that in the middle of the design process we had to redo a board because we had to add a channel to the recovery PCB.
So, what makes your team most different compared to other teams that work on Stratos IV?
Yeah, so this is a big debate in our team. We don't really do big test campaigns, or we may machine big parts or whatever. We make our stuff and we test it continuously. We test the different parts of the and also if there's a piece of software wrong, we can just fix it in no time. It's not one big part. We verify with like 5 tests and it's done. For us it's more of a continuous integration. It's never finished. It could always be better, and that's a big difference. So we could end up writing code till the day to launch. So for other departments, they usually make a tank or a combustion chamber, like a big part. They do some testing campaigns on it, and they have an iteration. And for electronics, of course, there's a big hardware part, but also software part. And also the hardware part it's relatively easy to change or to test things. If a certain circuit doesn't work, you can kind of tweak it or change it while it's still in your hands. And for other teams, that's not so easy. So they do their tests to validate the stuff, and we basically continuously develop until we find a solution that's good.
Two, one, pull.
Today we're standing at the open jet facility of the TU Delft. This is a wind tunnel that can go up to 30 meters a second and in which we test different parachutes for dare. The different types of parachutes we've tested today, or which we've focused on over the last few days, are the Disca band parachute and the Hemisphere ribbon brogue parachute.
DP, you can start the tunnel. Turning up the wind tunnel to 25 meters a second. 5, 4, 3, 2, 1. Pull.
After the unfortunate breakup of Stratos III, Delft Aerospace Rocket Engineering did not give up and started project Stratos IV, which is, as the name suggests, the 4th iteration of the Stratos mission. The goal this time is not just to break the European amateur altitude record, but to go to space, to break the 100-kilometer line and make DARE the first student team to achieve this feat. We as the Parachute Research Group support the project by developing the recovery system that will bring down the flight data safely. One of the parachutes behind me, the Disca band, is the main parachute of Stratos IV, and the other parachute is the drogue parachute, which is the Hemisphere drogue parachute, identical to one that flew on Stratos III.
The Hemisphere drogue ribbon parachute is a special parachute that can go up to high Mach numbers, and this is used in a lot of Stratos missions to retrieve the nose cone safely. It is also being tested for its high Mach capabilities on the supersonic parachute experiment aboard Rexus. This is a mission that will fly on the Rexus 28 sounding rocket in March 2020. The drogue parachute is made out of 150 different pieces of tape. So you can imagine it takes a little while to produce this thing. Currently we've got it down to about a week of production time.
So behind me is the actual test bench that we use to deploy and measure the performance of the parachute. As you can see, it's quite a sturdy design made out of steel to make sure that it doesn't bend and doesn't go anywhere during the tests. We have a 3D printed white canister on top that we can use to safely store the parachute and deploy it on command. But most important is the load cell where the parachute is attached to. That load cell feeds into the laptop so we can measure the drag generated by the parachute during the deployment and during the static behavior.
today we've tested the disc cap band parachutes, a disc cap band clustering, and the Hemisflow ribbon drogue parachutes under varying conditions. But in our next wind tunnel test campaign in May, we will also test the sequencing of these parachutes together in a Stratos and Spear configuration.
velocity decrease.
Yeah.
We lost the vehicle. Over.
Congratulations, guys.
So the titanium nozzle is indeed on fire.
Hello and welcome to the Stratos IV launch show. I'm Liz, this is Niels, who will be your co-host for today. We're here at Inta please watch along with us. We have plenty of content lined up for you and hopefully we'll be launching tonight as well. And welcome back to everyone who's tuning in after tuning in already last week with us. Niels, why don't you introduce yourself?
Yeah, so I'm Niels van Laarhoven. I'm the Chief Structures of the Stratos IV project. I'm a master's student and I'm studying aerospace structure and materials. What about you?
I'm Liz, everyone calls me Liz, not my full name. I'm a propulsion engineer for Stratos IV. I was the previous president of there, and I'm also a master's student in aerospace engineering studying propulsion and power systems.
So yeah, currently we are, as you already mentioned, we're at Inta in Mazagon in the south of Spain. And the Stratos IV team has been here now for about 4 weeks preparing for the launch of the Stratos IV rocket.
Today is Wednesday, and we're preparing for launch in a few hours from now. Please follow along with us, and we'll take you through all the steps and procedures that we need to still get to launch today.
So a little catch-up for the people that weren't here last week, Friday, when we had our first launch window. So basically what happened is that we sadly had to encounter a no-go in the launch procedures. This one reason for this was that we had a lot of delays during our procedures because we still were testing some things during the actual launch window.
Yeah, and we also had an issue with our load cell, which you might have heard about. So this was acting up and giving us inaccurate measurements. We thoroughly investigated the issue. Since then, we tested the load cell successfully and figured out that the load cell itself is behaving fine. And there's a few minor issues that we're still troubleshooting today as well. But today?
Yeah, so today we actually, we do hope to launch in a few hours from now. As you can see on the countdown tower up there, is that we currently are still at a hold because of this load cell issue that we are encountering. But hopefully, somewhere soon, that counter starts ticking again, and then you know when we will actually go into space.
Perfect. Well, let's talk about Stratos as a project and as a home. Niels, why don't you introduce what you would consider the goal of Project Stratos?
Yeah, so our goal as Project Stratos is to, with a group of students, actually build a rocket that is capable of some of the same things that government agencies and multi-billionaire companies could actually achieve, but then as students, with a small team, a smaller budget, and to actually kind of democratize space so that we all can go there. And how we actually try to do is by trying to break the European amateur altitude records for spaceflight.
Right, let's talk a bit about the tech of this rocket as well. We're dealing with an 8-meter tall rocket that is around 28 centimeters in diameter, so it's quite a big beast. It's a hybrid rocket. It's propelled by the hybrid Nimbus engine, which we developed ourselves, with an average thrust of 13 kilonewtons. We have a cold gas roll control system on board, as well as passive measures for countering roll control. Our cell's combustion chamber fins are made of carbon fiber. We have a twirling nose cone and parachutes as well made of composites, and we have a dual deployment system with a drogue and a main parachute. Our electronics are developed in-house, but we have a commercial flight termination system on board.
Yeah, so right now we would like to show you all an animation we made of basically the flight path that the Stratos rocket will take, where we go up into the air. They have a roll control kind of keep them stable. Then at apogee we separate, a recovery sequence starts, and then eventually we have a splashdown.
Well, that was a very nice overview of our trajectory, as you mentioned, Niels. Let's talk a bit about the history of Project Stratos as well.
Yeah, so basically, Stratos project now over 10 years ago, back with the Stratos I rocket. The Stratos I rocket was a solid two-stage rocket, and it was launched back in 2009 in Esbjerg in Sweden. With this Stratos I rocket, we as a society actually managed to for the first time get the European altitude record at 12.5 kilometers.
Well, after Stratos 1, there were Stratos 2 and Stratos 2 Plus. Stratos 2 and 2 Plus had a hybrid engine now, and it was obviously a bigger rocket as well. These were the first rockets that were set to be launched from Intisadea, where we are today as well. In 2014, Stratos 2 went out to Intisadea, but unfortunately had a misfire. This means that we had ignition, but there was no actual fire of the rocket. So for the next year, the team went back to the Netherlands, worked on the rocket, and this now became Stratos 2 Plus. And when Stratos 2 Plus came back in 2015, it launched here and set another record at 21.5 kilometers.
Yeah, so after Stratos 2 Plus launched, 1 year later, a group from Stuttgart, Germany, HyEnD, they actually broke all records at 32.3 kilometers altitude. And with that, we actually started the Stratos III project, and their aim was to take back the record to there. The Stratos III was one of the biggest, most powerful Stratos rockets yet. It was the follower of the Stratos II with a more powerful single-stage hybrid motor. Unfortunately, during 2018, we encountered an in-flight anomaly. And with this anomaly, we actually set forth to design the Stratos IV to counteract the phenomenon that we encountered. So basically for this project, for the Stratos IV, we have a lot of different departments. We have our structures department, our electronics department, propulsion, recovery, simulations, PR acquisitions, management, logistics. There's a lot of departments.
If you draw an analogy, how would you say, you can start with structures. If you take a rocket as a human, what would you say?
Yeah, so structures is kind of the body of the rocket. It holds everything together. Then we have electronics, which is kind of the brain, which controls all of it. We have electronics, that's what you said, the brain. We have propulsion, which is the muscle. Propulsion is the engine that actually gets us up into the air. The recovery system is kind of designed to bring back the rocket after the launch.
Catches you smoothly if you ever fall.
Yeah. And then the simulations is kind of the part of that predicts where are we actually going, the thoughts or something, I don't know. And then
PR acquisitions management, those are just yes, but they're absolutely necessary for the project for sure.
Yeah, and with that, we would also like to go into our Meet the Team video, where you can get to meet all the chiefs of these departments.
2, 1, 0.
I am Chief Propulsion of the Stratos IV rocket.
Sponsorship Acquisitions Manager.
The Joint Chief Electronics with the other Jasper.
So I'm the Chief Electronics.
Electronics Engineer.
I will continue with my treasurer responsibilities.
Chief of the Structures Department.
I'm what we call the Process Manager.
Chief Recovery of the Stratos IV.
Part of the recovery team. The lead engineer on the roll control system.
Head of Food Logistics.
I'm the Team Manager.
Chief Engineer. So what I didn't expect was how intense and exciting it would be.
Blood, sweat and tears.
Cherry on the tip of the iceberg, yes.
For working days and nights, every week, every day.
Seeing this launch is just going to make everything so worth it.
It's now the full circle.
I'm already smiling when I think of it.
It's just so cool. I love it.
Alright, so that was a quick overview of the departments we have in the Stratos project. But now let's take a look at what this project has accomplished in the last 3 years. So Stratos IV has been working for 3 years, as I mentioned. And so a lot of engineers have come and gone with this project, and a lot of people have worked on it as well. In the first year, this was when I joined the project, we had a lot of design work. So we took the design that we had for Stratos III, and obviously since there was an in-flight anomaly, we conducted investigations and kind of went from there to try to make a rocket that could have a successful flight and that we could eliminate chances of this anomaly happening again. So we had a lot of design work, we improved on the design, we had lots of tests. I went to a lot of engine tests in that year, that was really, really fun. And after that, we got to the second year release.
Yeah, so the second year is actually when I personally joined the project. During that year, we built forth on what the first year team already started on. We did further testing. We had a lot of components that they produced, which we could actually test and then possibly improve upon. And then also we did we started on the manufacturing of all the flight hardware. So that was kind of the second year and not the integration. But then at the start, like 2/3 throughout the second year, sadly we had the COVID pandemic happen. So COVID kind of slowed us down. We aimed to actually launch last year, but then because of that pandemic, we lost facilities, we lost production requirements, and we definitely could not host a launch campaign during that time. So that's why the launch got delayed by a year. And then yeah, this last year was actually kind of picking up where we left off when the pandemic hit, and then also the preparation for the actual launch campaign itself.
Yeah, exactly. I think it's really good that you mentioned COVID heals, because I think it's to no surprise that this has affected us as well as a society and as a project, as this has affected many people in the world. And I'd like to shortly talk a bit about that as well. COVID was obviously hard. It's difficult to build and launch a rocket if you can't be physically together, if you can't work together. But we took this in our stride and we tried to make the best of it. So we continued online work in there. So not only Project Stratos, but a bunch of other rocketry projects that were working continued their work online. We had a Discord server, and when you logged in in the morning, you could just see a bunch of different teams having their own meetings, people working, and it kind of kept that workplace mentality alive that we're really quite used to having. And that was really nice. And of course, it's not all about work. You have to get your social juice somewhere as well. So we had a lot of fun online events in the evenings, which really kept the spirit of the project going and it helped us. It was tough, I won't lie, and of course it brought delays, but that's sometimes how life is, and it's not something that we can avoid. So in the end, I think we came out of it a stronger and better society and team who knows how to deal with these challenges and learn to work in more hybrid formats. So that's quite nice. And we have a video to quickly introduce you to this topic as well and ask some of our team members what they thought of the COVID situation and how it affected them.
2, 1, 0.
COVID. The main issue with COVID was that we lost a lot of our production facilities. This meant that in the midst of a pandemic, we needed to search for new places and sometimes even methods to make sure that all our parts got produced. In the end, however, we managed to pull through with some support of some of our sponsors so that we could produce everything in time for the launch.
All the buildings we work in, they shut down. That was pretty problematic as a lot of my work is practical. Mixing the fuel with raw ingredients, you have to be there with 4 people. It's not something you can just do by yourself. That was a big issue for us. However, what we did, we all went home and we started working on all the documentations, all the computations that still had to be done, such that when we could actually access the buildings again, none of the paperwork had to be done anymore. We could just focus on all that practical stuff.
Compared to some other departments in the team, like the structures department, which needs a lab to work in, I could argue that we were one of the lesser affected aspects of the Stratos IV team, as a lot of the things we could do, we could still meet online very easily, we could still make social media posts, we could still communicate with sponsors. Although our edge, as you might call it, or our ability to do so was severely impacted.
So yeah, COVID was quite tricky, especially with the big lockdowns. Yeah, labs closed up, and our electronics stuff we need is in the labs, and not all students have a fully fledged workspace at home, so electronics progress stagnated. A lot of the physical stuff we couldn't do. We could write some code, but we could only test it in a limited sense, so it just came down to like documentation and code and that kind of stuff, but not really the PCBs or any of the electronic components. This last summer, everything was open up again. We could really, get the work and finish it. So that was really nice.
So I think it's impacted it on two fronts. First of all, being generally the team, how did we run? How did we run with our team? How did we work? How could we even access the rocket to build it? So that was a really big challenge, and it was mostly we had to think really creatively, as in, okay, where at any place can we do these certain things for the rocket? So where can we work on our electronics? Where can we actually access machines to still produce certain parts? Where can we get composite material for the rocket? Because now we didn't have one centralized workspace anymore that we could access, so we had to do it all over the place. But still, while doing that, make sure that everything afterwards would fit together, and that was also done safely and not like randomly, and not that things got lost. And then also, how do you do your meetings and all of that stuff. That was one big challenge. So not only just working from home, but also working in little workplaces, basically. That was one challenge that we just overcame by being creative. And then the other one was, we're going on a big campaign with a lot of people. So at max we're about 36 people. That's quite a large group. So how do you do that safely? Because normally you want everybody to be healthy and you want them to be safe when you're launching a rocket. But now you want them to be extra healthy because there's now an additional risk added into the formula. So for that was quite a tough one to figure. Okay, how can you still make the project work as best as we can, so that everything on the rocket side and the technical side is still done successfully and safely, but also that the people themselves remain healthy. So we took some inspiration from events such as the Olympic Games, Formula 1 races, big events, and then tried to translate that into what we needed.
There we go. So speaking of COVID, there's one thing I would like to quickly do, and that is thank all of the people who supported our crowdfunding campaign, even though it happened right in the middle of COVID and this pandemic. So I would like to thank everyone who raised money for us. Thank you very much. We raised almost up to 15,000 euros, and we greatly appreciate that. And if you would, for some reason, like also support future dev projects, then down in the description there is a link where you can donate some money to other dev projects.
Yeah, thanks. It's very much appreciated. So we also have a quick update for you on the procedures as they are so far. I've been just told by Mission Control that they are working on some more tests, and we will have an update for you as soon as possible, whether we know if it's a go or a no-go for tonight. So please stay tuned and keep you informed as we are.
Yeah, so speaking about procedures, I think it's nice if we kind of wind back the clock a bit to yesterday, when we actually started our procedures. So for the past week and a half, we've been readying the rocket for the actual launch itself. So we've been integrating everything together to make sure that everything is prepared. And as I said, like yesterday, we started with our launch procedures, and would like to give the word to Liz on that.
So the actual launch procedures for Stratos IV take 2 days. So yesterday morning, we started our first checklist, which is checklist alpha. And this is the pre-flight assembly of the rocket. And I have a useful tool here that I can explain this to you with. So we start with the different components of the rocket, which are already assembled. And they are ready to be joined together into one fully assembled rocket. So you start with the tank and upper skirt, which are already here, nicely integrated. And then you start with the electronics here below the tank in the engine bay. So you check the electronics, you assemble all the required things in the engine bay, and that's good. You do some final checks, you check out the flight termination system, and if that's all good, then the engine can be attached to the rocket. So engine is attached, you're all done on the bottom of the rocket, so that's quite nice. And then you move to the top of the rocket. Here in the upper skirt, you have the roll control. So once all of those are checked and good as well, then you can attach the separation system. And this, of course, also has some tests and electronics needed to be done to it. And the separation system ensures that once we reach apogee, the tank and nose cone can separate nicely. So once that's put together, you assemble all the structures and electronics in the nose cone tip itself. And once that's done, the final step is to slide on the nose cone shell, and this completes our assembly. You, of course, have also additional checks to make sure that everything is good. The chief engineer checks over the rocket, and then you get to the end of the first day of procedures.
Yeah, so as Liz just explained, after the first day we have our assembled rocket, but then this rocket is not ready for launch yet, as we don't do some more checks, and we actually need to get it up straight. So that's where checklist Bravo comes in. During checklist Bravo, which also happens at the start of this day, we take this rocket and we transport it to our launch pad, where we have the tower waiting for the rocket. So we insert the rocket in the tower, we do loads of checks to see that everything is looking good before we finish this off, and then at the end of checklist Bravo, we actually raise the tower so that the rocket is in the correct angle for the launch.
So then your rocket is ready, the tower is ready as well, but of course there's some more steps. You get to the third checklist, checklist Charlie. This is the pre-flight procedures which happen on the pad, so on the launch pad itself. And this is for checking some of the main actuators in the rocket itself. So you check the valves, you check the igniter, all of these important bits that need to move during launch to make sure that the rocket flies correctly. You also check the heater box, which powers our heating lamps, which we use to pressurize our tank. And once again, you check the flight terminator system on the pad with the rocket in the tower. This is very crucial for safety, and we take this very seriously.
Yeah, so after we've done all of those checks and we actually find out we are ready to launch, we get to the point where currently we are at, which is checklist Delta. In checklist Delta, we actually hook up the kind of dangerous stuff to our rocket whilst we still can. So we hook up the bottles with nitrous oxide, which is an oxidizer for our engine. Furthermore, we actually arm the flight termination system so that in case normally we can actually terminate the rocket and will actually terminate. And then lastly, we also hook up the spark in our engine that actually makes our engine fire. So in checklist Delta, all of those are hooked up, and then at the end, the pad will leave the crew. The crew will leave the pad.
Exactly. And if we know that we are a go for launch today, then after this, we'll go to checklist Echo, where we do the filling and pressurization of the tank. And after this, you shortly get to launch, but we'll make sure to keep you up to date with the procedures as we go along today.
So being the launch site for both the previous Stratos II Plus and the Stratos III, and now also the Stratos IV, but our team would like to thank and give a quick shout out to one of our biggest sponsors, and that is the National Institute of Aerospace Technology here in Spain, also known as INTA. Our team has been working with INTA personnel here at the test center for the past 4 weeks in order to prepare for this launch. Our team has found to base a truly modern facility which can accommodate our launch and give us the best support around it. We are extremely grateful to INTA personnel, which is helping us with this launch and to plan and organize everything around it. We just want to give a big thank you on behalf of the entire Stratos IV team and there as a whole to INTA.
I think as a student, it's also wonderful for us to be here and see this really organized and professional workings, and it's giving us a lot of experience that we can never get from anywhere else.
Definitely.
So let's move on to a slightly different topic. Maybe for the watchers, we've talked a few times about DARE, we've talked about Project Stratos. Let's clarify how these link to each other. So we are here launching Stratos IV, which is a rocket that is a part of the Stratos project. However, the Stratos project itself is part of a bigger society that we call Delft Aerospace Rocket Engineering, which we are all part of. So Niels, why don't you give us a quick intro to what DARE really is?
Yeah, so as you just said, Delft Aerospace Rocket Engineering, the name kind of tells it. DARE is a society all based on engineering around the aspect of rockets. So our society consists of over 200 passionate students at the TU of Delft, and we are here working on rockets, on projects around it, around parts of rockets, or anything to do with rockets, and we are very passionate about this. So we as a society want to give the opportunity for students to actually get some practical hands experience with rockets and everything around it. So that is kind of the aim of DARE, to allow students to actually get this practical experience.
Yeah, and DARE has quite a long history at this point. So DARE was founded in 2001 as part of a larger society of aerospace engineering students at the TU Delft. However, from 2010 on, we are our own society as well, who is fully devoted to rocketry. And I'm sure there's many great things to come for DARE in the future, and I'm really excited to see what we get up to. To quickly go over some of the things that DARE does, aside from Project Stratos, let's look at some of the projects that we have in DARE itself. So we have, next to Project Stratos, we have another large project that we call Project Sparrow. So at the end of kind of this, coming up to this launch campaign, it was the end of the Stratos project, because currently right now we didn't consider it enough of a technical challenge to continue shooting this higher and higher. There was a group of people who thought, hey, maybe it's time for a new type of technical challenge. And out of this idea grew Project Sparrow. Project Sparrow aims to develop a liquid rocket engine, which DARE has not yet successfully hot fired before Project Sparrow, that is. So we've done a lot of hybrids, we've done a lot of solids, but this kind of completes our roster of different kinds of engines. And this team was set up last year and worked over this past year to achieve a successful hot fire of a liquid engine in August, which was quite fantastic to see. They really had amazing, huge progress over this year, and we're really quite proud of them. And this project is, of course, continuing as well into the next year. And next year, they are aiming for a full duration burn with the hybrid, with this liquid rocket engine as well, and also with a 3D printed chamber, not in a battleship configuration. So really excited to see what they get up to. And we have some highlights as well from their last successful campaign, which we can show you now.
So as you can see, that was a nice video from the test campaign of Project Sparrow. We would like to congratulate them on their success. And with that, I would like to continue to wonderful, because besides Stratos and Sparrow, there's more than just these flagship teams within there. We'd like to highlight one of the smaller teams within there, and specifically Yoke. So Yoke is this competition in Portugal that is an annual competition where different rocketry teams from around Europe actually participate in. And actually last Friday, for the first time ever, DARE actually competed in this competition. So for this competition, we made a rocket with two 5 kilonewton solid motors and a aluminium sheet metal body. This rocket is actually based on successful CanSat launchers. It's a bit of a beefed up version of these launchers. And as a payload, we actually also had a Lunar Zebo, which is a student-developed ultralight lunar rover. We had that on board to test its parachute system, I believe. So this rocket was built for an apogee of 3 kilometers, and they had a successful main parachute deployment. So I think we would like to show the video of their launch right now, for those who missed it last week Friday.
Visualization.
Appears to be
Anomaly.
I can confirm that this did in fact slightly after all. Apologies for the slightly mismatched video, but yeah, congrats again to the Euro team. Really great achievement. They had successful ignition of 2 engines side by side, which is quite cool. Successful main parachute deployment, as you mentioned. You might have noticed there was a bit of an anomaly in flight, and they're investigating that as well. But we're still super proud of them. I think really cool stuff, and it's cool to see that they can really sustain 2 launch campaigns at the same time, and also on the Iberian subcontinent, which is quite cool. So yeah, these are just some of the projects in there. Later on, we'll go into more depth and introduce you to some of the other projects in there, so stay tuned. But right now, we'll take a short break from the live stream show, so we will be back in only 5 to 10 minutes. Thank you for watching this.
Also, before we start the break, feel free to put any questions you have in the live stream chat. If there's enough questions, we'll go over them after the break, and otherwise we'll address them later. So see you in a bit. Hello, welcome back everyone. As you know, I am Niels, and this is Liz, and this is the Stratos IV launch live stream. So as we said before the break, we asked for some of the questions. We have a few, so we're going to do a very short Q&A right now with those few questions we have. So first of all, there was the question, how is the weather looking today? So the weather today is looking all right as of now. Maybe towards the late night, the weather is going to go a bit downwards, but for now, we're looking really good. So as it stands now, we can definitely launch.
We have multiple check-ins through the day for the weather. So beginning yesterday, we already checked out the weather today. But of course, you want to update that throughout the day. There has been a high-altitude weather balloon that has checked the winds up there, and go for launch on the weather so far. So it's looking quite nice.
Then there was also a question about where we get our ambient pressure data. So in the nose cone, there is 2 pressure sensors that actually measure the pressure in the recovery bay, which is connected to the ambient air. This is where we get our pressure data for our recovery parachutes and the times for those things.
And we had some general questions about recruitment in there, or people wanting to do courses, theses, internships, whatever. So right now, there is a society of students at TU Delft. So if you are at TU Delft, or maybe in one of the schools close to there, feel free to contact us. We can see if we can, facilitate you joining a team, or maybe a few people have done internships with us. But we cannot, unfortunately, sustain full courses or online internships and theses for people abroad. So we are a society for primarily TU Delft students right now. I hope that clarifies some of the questions that we brought.
Yeah. So with that, we would like to continue to the next segment in the show, which is kind of talking about the technical details of the Stratos IV rocket. So I think we have a nice animation lined up for this, so that kind of shows parts of our rocket and how they fit together.
Yeah.
If we wait 1 second.
Yeah, of course, we have the whole assembly done up in computer-aided design. And so this shows a kind of overview of this.
Yeah. So as you can see, the rocket has a load of parts. In total, I think there is over 300 different parts in a rocket, of which there's also like over 150 different bolts and nuts and washers and things like that to all keep it together.
Yeah, so this is quite a nice animation. You see, okay, all the electronics here, you saw the different parts of the rocket, and we'll shortly go into explaining all of these different sections while there's links to the different departments that we talked about. So we'll kind of quickly go over some of the different sections of the rocket, what is a part of them and why we need them, and so on. And let's start with the engine, which is my turf, really. I'm a propulsion girl, always have been. So the Stratos IV rocket is powered by the Nimbus engine, as we know, also known as the DHX 400 as well. So it has an average thrust of around 13 kilonewtons and a peak thrust of over 25 kilonewtons. The diameter is 28 centimeters, and it is a hybrid rocket. We have a carbon combustion chamber and a 3D printed titanium nozzle, which is supplied to us by 3D Systems, thank you very much, with a zirconium coating from Oerlikon, and a graphite insert as well on the throat for managing some of the highest heat loads in there. So the engine overall consists of, going from the top to the nozzle side, you have a injector, combustion chamber where the solid fuel sits as well. You have a mixer and you have a nozzle. Okay, and I'll quickly go into some of these different systems, talk about the overall design and manufacture of the engine. So why hybrids in the first place, and what's really makes the difference between what kind of engine we choose? So largely for this size of sounding rocket, you have a few different options. You have liquid, solid, or hybrid engines. What this means, this pertains to how you store your propellants. So in a liquid rocket engine, your propellants, this is your fuel and your oxidizer, are both in the liquid part. In a solid engine, your fuel and oxidizer are in a solid grain together, that ignite and then they combine. And in a hybrid, it's a combination of the two. For us, that means that our fuel is in solid state. So we have fuel grains inside of the engine, and we have a liquid oxidizer, which is nitrous oxide that we feed into the engine. These then react, energy is produced, and we convert this energy into thrust in the nozzle. So maybe to talk a bit about the choice as well. Liquids often have higher performance, but the propellants often need to be pressurized, sometimes in cryogenic conditions, and they can be very reactive and hard to handle. Solids are robust and simple, but you can't throttle them like you can liquids. You can't stop the burn once you start burning a solid because you have all your fuel there, so it's really hard to, you can't stop the burn once it goes, right? And solids also sometimes tend to have lower performance. So a hybrid is ideally the best of both of these worlds, sometimes can be the worst of both of these worlds, but you try to avoid that as much as possible. You still have the ability to throttle the engine by limiting the oxidizer flow into the engine, but you only need one pressurized tank for the liquid oxidizer, and the fuel grain itself is far easier to handle. And it's also one of the safest ways to make it handle propellant for us, because it's really like, you're not gonna, that solid grain, you're not gonna ignite it by any measure, because unless you have that really high oxidizer flow from the tank, you're not gonna burn it up easily. So this was the main technologies for DARE at the time that Stratos II was starting out. Hybrid's development had been happening for a while, and it made sense to try and put this engine on a rocket, right? So that's one of the reasons that we came to this point. And since Stratos II and III, the design of the engine in terms of its fuel and oxidizer has been largely the same. So for anyone interested, as I mentioned already, we use nitrous oxide as our oxidizer, which is simply known as laughing gas. So it's used in, medicinal applications and such, but we also use it as an oxidizer. And our fuel itself is not made of some super exotic ingredients. We make our fuel out of paraffin, which you might know as candle wax, out of sorbitol, which is just a kind of coffee sweetener, and then we have aluminium powder in there. And fun fact, all of these ingredients have E numbers in their classifications, so technically the fuel is fully edible. Wouldn't probably taste very good, but yes, it is a very simple mixture. But this is enough to propel an engine of the size of Stratos, which is quite cool. So how do we make an engine? Let's talk about that for a bit. We produce the fuel ourselves, so we mix all of these components together in this huge vat, manually stirring it. It's a lot of physical work. And then we cast it into these special jigs that ensure that we have these cylindrical grains with a hole in the middle. And that forms your, combustion chamber where you'll inject the oxidizer and have burning as well. Then we cut these grains because we can't cast a full-size grain at once. That would just be difficult in many, many ways because the full grain of Stratos is quite long when you compare it to the rocket. So we take around 3 grains of this size. We cut them to the proper size, and then we adhere them together, kind of melting fuel in between them to make sure that they're adhered. Check that the fuel is of high quality by taking it through an MRA scanner. This means that you can see if there's any sort of cracks in it, any bubbles forming. You don't want that. So we make sure that is all good, and then we put those grains into the casing that becomes the engine and the fin cam. Right? We produce the mixer, injector, and all the manifolds that are required to attach these things together. We produce the carbon combustion chamber, which Niels might be able to tell you more about later. We put the grains inside the engine, as I said. We build a pre-chamber as well, which sits above the grains, and we build this out of cork and part. We insert all the required components from the mixer to the injector and the nozzle. And then we go and fire it. We always test our engines, and we really make sure that we have successful tests before we ever get to a launch. The nominal burn time of this engine is 38 seconds, but you might have heard about this before. We are cutting this down to 28 seconds. So what this means is that this engine is more powerful than what we are currently firing and could take us higher. However, with the safety range that we have and our current capabilities, this really dictates the range. So we've tested the full burn. It's quite amazing. It's really an emotional thing to be there at an engine test. You feel the rumble of the engine in the bunker next to you. But yeah, we know that this engine is capable of more, but because we are wanting to stick to a safe launch, and because we are limited in our capabilities of what kind of launch sites we can go to as a student team, we are capping this engine's burn at 28 seconds. And we have lots of fail-safe mechanisms to make sure that this is truly capped, and if something doesn't work and the engine keeps burning, then we have measures to make sure that the rocket does not go any higher than we want it to go. So don't be worried about that. So yeah, this is a big engine. It's been a real pleasure to work on it. And maybe to wrap this up, before I tell you some of the tech details once again, I'd like to talk about some of the improvements that we've made since Stratos 3. Because as I mentioned, the fuel we use is largely the same, right? But the carbon combustion chamber, for example, is a big improvement that we've made since Stratos 3. This saves us a lot of mass, which is really good for, you know, the overall trajectory and what kind of apogee we can reach. We have a 3D printed titanium nozzle. Thank you to 3D system for this, which really saves a lot of mass over our last graphite nozzle, which is much heavier than a nice shaped 3D printed titanium nozzle. And we have a circuit component and also a graphite insert for some of the parts, so this is near the throat of the nozzle. We've improved our processes, so making an engine is a lot of different steps of manufacture, and it takes a lot of hours and a lot of people. So we really improved upon those, tested different forms of, you know, heating and kind of conditions we can keep the grains in, such that we ensure we get the best quality grains after we cast and so on. And of course, we've just had experience in building and testing the engine, which is really helped us a lot and made us work more efficiently. So to summarize, we have an engine with 13 kilonewtons of average thrust, a peak thrust of over 25 kilonewtons. We have 226 kilograms of propellant on board, and the specific impulse of the engine 180. However, I'd also now like to give a quick shout out. As I stated, hybrid technology development in DARE started around a decade ago, and it has been continued from team to team in the Stratos project, and will probably be continued after the Stratos project as well. Similar to most other rocket technologies, it was not a technology that was easy to develop, and the engine itself was not easy to develop. But we persevered through, you know, lots of delayed tests, burn-throughs, misfires, numerous setbacks. However, we could not accomplish this alone at all. It's this sort of consistent drive that makes one of our largest sponsors, Air Liquide, really, you know, important to us. Being one of the world's leading suppliers of industrial gases, Air Liquide supplies the nitrous oxide that we use as oxidizer for our Nimbus engine. Our Air Liquide sponsored the first Stratos rocket with a hybrid engine, which was Stratos II+, which launched from Intessadea back in 2015. The launch set the European student rocketry altitude record of the time with an apogee of 21.5 kilometers, a record that we are also striving to break here today. So we'd really like to sincerely thank Air Liquide for their continued support, as we have broken records with them before, and we are looking forward to doing so again. And finally, to close off this little engine section, I'd like to show a video of an engine test. I already told you how amazing it feels. Niels, I think you've experienced one as well, right?
Yep, I have.
So maybe you can have a bit of a view of this as well. So let's pull up a video of a Nimbus.
5, 4, 3, 2,
350. So the titanium nozzle is indeed on fire.
Alright, that was quite an exciting video. Always brings a smile to my face to see things like that. But yeah, I've had my rant about engines. I think it's time to move on. Niels, what about your field of it?
Yes, so now it's time for me to shine. So as I said before, I'm chief of the structures department. So let's talk a bit about the structures in the rocket. So as mentioned before, the engines are the propulsion is kind of the muscle of the rocket, and the structure is the bones keeping it all together. So my plan for this section was just to kind of go top to bottom to the rocket, mention some interesting things, because otherwise we would be here for ages talking about all the structure. And I think there's only a fair few people that will actually find it interesting. So for that, I'll bring a friend the Lego rocket back. So yeah, I think we just go top to bottom. So we start with a nose cone. So an interesting fact to note about our nose cone is that a nose cone is actually an airtight system. Because inside of our nose cone, there's some electronics, especially for the telemetry, that produce quite a bit of heat. And if we are not deep tight in the nose cone, that means that there's no convection of the heat generated by the electronics, and we will actually fire them. That's one of the two reasons we keep our nose cone leak tight, and the other reason is that after we had separation at apogee and we want to find back the nose cone, we actually want it to float, otherwise the retrieval guys are going to have a very hard time actually finding it back. So that's the second reason. So our nose cone is made of a Twaron composites, which means that it is radio transparent for the aforementioned telemetry. Furthermore, we have a 3D printed steel tip, which actually has a thermal sensor in there as a payload. So that's also quite nice to mention. Then the next section is this small orange section here, which is the recovery bay. In the recovery bay, it houses our parachutes of the recovery system, which we'll go into depth to a bit later in this talk. So the recovery bay, it has a carbon fiber shell. As you might notice during this talk, we like carbon fibers. They're strong. They are also lightweight, which is very beneficial for a launcher like the Stratos rocket. So inside there are two canisters for our two main parachutes. So there's the main parachute and the drogue parachute. So there's two carbon fiber composite canisters for those two, which are held together by a plate of a carbon fiber centric structure. And there's also a bar, which is a 3D printed steel bar, which actually holds the one over here where we actually separate the rocket at apogee. How this system works is actually quite neat. So there's basically this spring steel clamp band around the rocket. So what we do at apogee is we cut a bolt that is holding the system together. And at apogee, it kind of springs open, and then it disconnects the tank from the recovery bay. After this happens, there is 4 very powerful springs in the tank section that kind of shoot off the fuel from the tank so that we have separation. And then this section will be recovered with the aforementioned parachutes, and this we will not track anymore. So then we get to the bottom of the rocket. The real meat is the actual tank. So as mentioned before, by lift, we need to store it somewhere. So this tank is a giant pressure vessel where we actually store this oxidizer. So oxidizer, it's stored at 60 bars, so there's quite a lot of pressure. So the tank consists of an aluminium line, which is then wrapped with carbon fibers for the actual strength to hold it together. So that is the tank. And then one thing I forgot to mention is that up here we also house the roll control system. So the skirt on the top side is a bit long to have room for the system to sit in, but it's 4 little thrusters, which we'll go into in a bit on how they work. So then to the bottom of the rocket, these are the 2 very massive parts, and there's this kind of lightweight part in between. So it's very important to make this part very rigid, otherwise you get it's not sagging. So here, 2 interfaces. It's very nice to know that these are conical interfaces. So what that means is that when you put them together, the bolts are it's like a slight bit of an angle. This kind of makes it self-align when you assemble it, which is really nice for both stiffness and also alignments. Let's see, I think that's most of the interesting stuff about the engine shell. And then the last bit where we are proud of the circuit component activating the most basic is the carbon fiber composite combustion chamber, as this already mentioned. So this is basically a big carbon filament wine machine. It's just a thick layer of carbon fiber filament. So this chamber is when you actually, after you've made it, you can easily by yourself lift it because it's so light. Well, before we used a thick aluminium tube to hold the engine. Now it's this light carbon fiber tube which you can carry.
Niels really improved our lines, so that's I'm sure.
Yeah, well, it's mostly done in the first year of the project when I wasn't really part, but I've been part of the production of a few of these things. Also, a nice thing to note is that these things generally are more circular than the aluminium casings that were used before, which means that a bit noisy compared to the previous aluminium chambers. Yeah. Furthermore, on this section, we also have fins. They are not quite scaled in this Lego, but create them slightly bigger compared to Stratos II. So what this means is these fins are in aluminium honeycomb with carbon fiber on top of it again. And since it has some more aerodynamic stability compared to Stratos III. This means that overall we should have less active a bit. Yeah, I think that is mainly it for the structures. Is there some part you think I missed out? Because I can ramble about this for hours, but I think at that point people.
Did you talk about the nose cone tip?
Nose cone tip, yeah, they still.
Yes.
3D printed.
I think that's a pretty good summary. We also have news that we have a message from Mission Control, which is quite special. So I'll read this out for you. And I'd like to say that we are a go for continuing the launch. The Nozzle issues that we were having has been resolved to a level that INTA has accepted for us. One of the rings was misaligned, and this was not solved by removing bolts as we were trying before. This removed some of the bending moment, and this gave wrong measurements, which are now correct. There are still slight internal static friction forces, which mean removing a given mass results in a less accurate reading, but this does not pose a problem for continuing for us right now. So, finish up some of the last bits of checkpoint Charlie we had, move on to checkpoint Delta, and on to checkpoint Echo afterwards, which is already filling and heating, which is quite exciting. So we'll make sure to keep you up to date with procedures as we go on.
So does that mean that at some point soon we will start seeing the countdown timer actually go down?
I hope so.
That's perfect to hear.
Really exciting stuff. Let's see if we have had any Q&A. I think a few questions that have come in here.
Yeah. So I think this is a question for you because it's engine related.
Yes, indeed.
Yeah, there is a question. How do we actually ignite the engine?
Yeah, so we have an igniter cells, which is kind of like a squib with really black powder inside it, and it's packed in a bit of steel wool, and it sits inside the bucket. So once the engine itself is igniting, it shoots out the back of the engine as well, and then the fire happens.
Yeah, so that's first bypass line. Let's a tiny bit of oxidizer enter the engine, if I'm correct. Yep. And then once that spark actually hits and starts igniting, that's when we open our main valve and the main flows.
There's maybe also a fun little story to tell here as well concerning the igniter and tests we had in the first year, which is teaches you a bit about what your igniter really does during an engine fire. So one of the times that we went to test, we had a new sort of control boxes that we use that sits by the test stand. It takes in the measurements from the different sensors on and controls the engine. We call this the radio, but it's really just a control box that connects to everything in the bunker as well. And so we had a new one that was revamped, and it was nice and pretty and shiny. But when we fired the engine, we counted down. We counted down to ignition. Engine seemed to fire, but nothing happened. Right. So it was a misfire. The igniter had blown out, but the engine did not seem to fire at all. So main valve seemed to have opened, but that just nothing was happening, and we were very confused. What happened, right? And so we troubleshoot this afterwards, and it turns out that actually the main valve line, so this was fired on the same line as the igniter. But what this means is that when the igniter gets its power and its spark from the same line as well, when we ignite the engine, it shoots out the back. There's just so much energy produced in that ignition that when you shoot the igniter out the back end, what's going to happen? You're going to short the line. And when you short the line, well, your valves, as always for safety, should return to their standard position, right? You don't want to lose power and then have your engine firing. So when you lose power, the main engine shuts down, or the main valve, shuts down, and then you don't have a fire. So after that, we knew to never put those on the same line again. Yes. Right. What else do we have here? We have a question about again, where do we test our engines? So for Stratos, we test our engines in the Netherlands on the location, and this is pretty fine. I'd also like to give a quick shout out to the place where we test our Project Sparrow engines at Woensdrecht in the Netherlands. We're really thankful for all their support. Site that supports our operation, and it's really cool to get to go to an awesome place to really test our engines in a proper safe setup.
With that, we should continue to our next which is roll system. I think that you want to talk about this?
Yeah, all right. Then let's go on with roll control. I'll get our little helper once again. So let's talk about why we need control first of all. So roll control is part of our sort of two solutions for solving the anomaly that we observed in Stratos 3. So one step, some of the steps we took were passive and some were active. So since you can't really quantify how much the passive changes you make affect the rocket, and we'll talk about this later as well, we also decided to put in an active component, an active system that you can really test to see if you can help with this. So the roll control system aims to counter the problem of pitch-roll coupling. And what this means is that it aims to counter the roll when it gets too high and keep it within a given boundary. But let's start by talking about roll-pitch coupling as a whole. So a rocket has many ways to move its flight, right? It doesn't just go straight up. It has many ways to kind of move on its own in this time. So if a rocket is going up, it can rotate on its long axis like this. It can move, say, in this axis coming towards you, or it can move to this side, in this axis going to the side, or any combination of these, right? So for the sake of simplicity, it's not really always the case, but we'll assume right now that this, which we call pitch, and yaw, well, depends on where you take your, we'll say that these two are, and then we call this thing roll, because it's rolling around its axis, right? And so in these different sort of planes of movement, the rocket likes to move at a certain rate. This is kind of like when you have a pendulum with a grandpa clock, it likes to move at its own pace that it is made for, right? If you just start to over-push a pendulum too much, it tries to settle to some place where it is happy. And our rocket does this as well. This is an intrinsic property of the rocket, which is known as the natural frequency. So once a rocket launches, you starts from this is kind of inevitable because you can't make the rocket fully symmetrical. The different loads on the rocket might be bending it one way or the other way a bit, and you can't really avoid it. So it's going to start rolling, right? And if it starts picking up this roll rate, at some point it's going to be rolling at a rate that is equal to the natural frequency in pitch. And it really likes that. It really likes to be at that point. So once you have these two matching up, they really start to amplify each other. And if I show you how this works, if you start kind of rolling and you are also pitching, and these two amplify each other, what this means is that you will start making these sort of circular patterns. And once this gets very, very fast and very, very violent, your rocket will simply flip on its side like this. And a rocket does not survive that. No matter how stiff, no matter how well Niels has done his job, a rocket cannot survive that going up at launch. So once it breaks up like this, you have aerodynamic breakup, which we observed in Stratos 3, and you lose your vehicle, right? So we want to stop this. Right, so let's talk about, actually, let's look at some of the passive measures first.
So you mentioned that one of the things we really strive for with a structure is to make sure that it is as stiff as we can get it. Because you can imagine, like, if the rocket is not stiff, if it's kind of a bit of a banana, as we like to say within our society, then it's kind of flexes more. And if a rocket has more energy to kind of flex, that means it will also easily start rolling due to small misalignments. And once we start rolling, that, as we described before, translates into doing this and then eventually fall. So that's one. We try to make it more stiff. And the second thing we did, like as a passive measure, was to make the fins bigger, like Stratos III. So bigger fins means that we have more, a more dynamic, a more static stability, which means that there's less of a chance that we actually start to fall into this dynamic instability. And then the last thing we try to do is actually try to quantify what the offset is of the center of gravity of the rocket. So basically, by trying to get it to as much to the center as possible, means that we have a less of an offset in our thrust factor. You can imagine that if the thrust factor is straight, we just go straight in. But if it's at a bit of an angle, a bit misaligned, that's when we actually start to get instabilities and we start rolling. So that's some of the passive measures. And then if you can explain some of the active measures, Liz?
Exactly. So as I already mentioned, some of the passive measures are really hard to quantify. I mean, we don't have the resources to launch a Stratos rocket in order to test whether our passive measures work. And sometimes this is what is done for projects like these, right? But we cannot allow that. So since we can't fully quantify if these passive measures will be enough, we also decided to put on board an active system. And this also provided a nice, interesting challenge for the newly formed roll control department of the propulsion team. So roll control has been through a lot of designs in these past years, and I'll talk you through quickly some of them. So we started with the general idea that we wanted to control the roll rate of the rocket. So we didn't want to say spin up. In case anyone is interested, it basically didn't make sense to us because we couldn't quantify the natural frequency of the rocket, which would also, again, have to be done with either really expensive testing equipment, or we'd have to launch a rocket to figure it out. So it didn't make sense to do spin up where you try to go and spin at a certain rate that you bypass the natural frequency, right? So we took the active control, and what this means is that we try to keep the roll rate not too high, not too low, but within a range that is acceptable. You don't want it to be fully stable or fully dead still as well, because the roll kind of helps you actually in its stability as well. So we keep it within a small margin, and how this is done is with two thrusters. So you have two thrusters in a pair. If you struggle too much, then the thrusters can shoot and make sure that you get slowed down again, and this keeps it within this range. So we started with a hot gas thruster system, which was supposed to be decomposition of nitrous over a catalyst bed. So it made sense. We were using our oxidizer, right? Nitrous oxide, also in our roll control system. This would be nice. We would have to have another tank, more work for Niels, and it would seem like a really good idea. However, these types of thrusters have not been demonstrated, not to enough thrust. I think the highest experimental development is up to, I think, 2 Newton thrusters, so they're quite small and they haven't really been demonstrated yet. So we took the challenge. We decided to try these. However, this posed a challenge quite soon. So we couldn't achieve decomposition because our temperatures weren't reaching hard enough, and so we kept working on this system, trying to get the heat up. Really, we had heating coil in there and everything. And once we actually got to ignition and we saw a little decomposition, it was actually so hot that the other the components of the thruster were getting scorched. And so at that point, you don't have any more material that you can use because your system is so hot. And then that doesn't make sense either if you're putting in so much thermal control to keep those little thrusters safe. Then we went to another really interesting type of thruster, which is a little hybrid engine thruster, which was burning 3D printed plastic. This was a really cool system, and while some tests had been done on it to show that this is successful, we simply did not have enough time to make it work. I mean, this change made, it was already into the second year, and there wasn't enough time to make sure that this is all integrated into the rocket, tested successfully. And so finally, we arrived at a cold gas thruster system. This is a very simple, very robust system. It's not maybe as shiny and novel as the hot gas nitrous decomposition system, but it works. It's lower efficiency. It's a cold gas system, which means that you're not decomposing anything. You're simply taking a cold gas and you're passing it through the thruster, you're passing it through the nozzle, and you're accelerating it to produce some thrust. So, of course, since you're not burning it, it's not as high efficiency, but it is still doable. But it's a simple system. At this point, it really made the most sense to use this. And I think overall, it was just a learning process. You get to try these different solutions, maybe learn a bit about how to take these types of design decisions and what you should consider in them. And I think it's also interesting to think about how, for a commercial rocket, you could be developing a system for years on end. This final system that we arrived to was developed in less than a year. So we had a lot of chances with different systems. And at the end, we still have an active system on board that we are flying with us, and that will hopefully help us counter some of the issues that we saw in Stratos III.
So with that was all about vol control, and with that I would like to announce a 5 to 10 minute break again, because we have talked about a lot of technical stuff by now, so I feel like people at home also kind of deserve a break, or talking about all these intricate systems and things.
We're having fun, but a short break. I'd like to once again, first of all, thank everyone that took part in the crowdfunding in spring. That really helped raise money for the Stratos campaign, that helped bring us here. We couldn't do this without you. Thank you so much. And I'd like to remind everyone that there is a donation link in the description if you would like to continue supporting us and Dare in all of the projects we will continue taking on. And finally, before we go off, Q&A is still live. We are very happy to answer your questions, so go ahead and shoot and answer them once enough have gathered up.
Yeah. See you after the break.
All right, welcome back, everyone. We are here at the Stratos IV launch show. Thank you so much for joining us. I'm Liz, this is Niels, and we're continuing with some of the technical details of the rocket, and we'll actively keep you up to date with any of the procedures that change and what we're up to in there.
Yeah. So during the break, we actually got a question about our payloads. So as I mentioned before, one of the payloads is a thermocouple which is embedded in our steel 3D printed steel nose cone tip. This thermal sensor actually kind of measures how hot the tip will get during the flight, which is really valuable data both for the guys that make the tip, but also for us. It's nice to know. Secondly, we have two, as we call them, slam sticks on board. These are little payloads by NLR, which is the Dutch aerospace facility. But basically, these are little vibration sensors. So they have a sensor with them. Once we pull 7.5 G is what they configure to. This is just below our lift-off G-force. So once they sense that, they actually start recording the vibration data. So with this, these slam sticks, they will record our vibration data both in the lateral and in the lateral and in the longitudinal axis. And then if we actually recover a nose cone, that means we get both of these sensors back. And then we can read them out and see what vibrations we had during flight, which is also really nice to know.
And I think this is a really interesting point to mark as well, that we are not, or as we talked about our goals, about democratizing space, and we're also kind of going for this altitude record again, hopefully, but we still have a mission as well, and we are flying payloads for other institutes. It isn't just a rocket that is flying up to fly up. We are providing others a chance to test some of their hardware, which is quite nice for us and for them as well. All right, so let's continue with the next department that we'll be talking about, and this is electronics. Rockets need electronics. You can't get away with it without having them. But to me, electronics is a bit of black magic. To many of us that are aerospace students, it is. But we have a lot of very talented electronics engineers in the team. And I'll try to give you a short intro as much as I understand, and then we'll see a video as well. So, yes, as I mentioned, electronics are really needed in a rocket to control all the different moving bits. So you want to control the valves, the various sensors, record data from the sensors, and store it in your rocket as well. Most electronics that we use are produced in-house. And the electronics that we have in the rocket, if I could have the Lego one as well, we have them in various places in the rocket. So these are kind of two brains that the rocket mainly has, is in the nose cone up here, and then in the engine bay as well. Because as you can imagine, for the engine control, you need a lot of different systems to make sure that the valves and all the feed systems here work. And in the nose cone, you have a lot of different bits like the flight computer for recording data and for all the recovery systems and so on. So we have a lot of electronics in various places in the rocket. So for the roll control system, the electronics team also developed the algorithm that we use for making sure that the thrusters fire at the right point, and this has been tested as well, which is quite cool to see. So even if you want to test this algorithm, you could also just rotate the roll control section as well and see the valves actuate as it tries to keep it to a certain roll rate, which is really quite awesome. They also configured the different timers for recovery, for making sure that the parachutes deploy at the right time. So the drogue is with a timer, the main is with a combination of pressure sensors and the timer as well. But we'll talk about this later in recovery as well. And I'd say that electronics are needed for pretty much every single system in the rocket except for maybe structures. They're really an invaluable part that is interspersed throughout all the different components. And now we have a video to show you with one of the electronics people that we have working on the rocket as well. So hear from him how we do this step. And we'll pull this up right in a second. Yes, thank you.
2, 1, 0.
5, 4, 3,
So I'm Jasper Jonk, I'm the Joint Chief Electronics of the Stratos IV. Together with Jasper, Jan and Gilles, we make the electronic system of the rocket. So yeah, first of all, the team, Jasper, Jan, and Jillis, they're really nice, good company to work with. But especially what I like most about the electronics is sometimes something doesn't work for some obscure reason, and if you then figure out what it is and then fix that problem, it like massive excitement to fixing it, and it just feels really good. And just seeing the rocket now with basically all the PCBs working together, doing the job, but still talking to each other, it's great. Good that you just light and it just shoots up. But it would be pretty boring if you do absolutely nothing from the time that you lift it off till it splashes down. It's just flight, nothing happens. If you want your rocket to do something, like gather some data about the flight or deploy some parachutes to recover it, you'll fairly quickly need some electronics, and that's where we come in.
The function of your electronic system and 3 main points.
So for 3 main points, the system is divided in 3 different sections. So you have the bottom section, which just open the valves and takes care of the burn state. So is the rocket on, is it off, should the valve be open or closed? Then in the middle you have the bleed valve controller, which is also houses the roll control system. So if the rocket spins too far to the left or too hard to the right, it tries to compensate. And then at the top you have the recovery and nose cone section, which houses the parachutes and all the sensors for recovery. So for electronics, yeah, we make our own PCBs. So we first draw up our initial schematics, saying, okay, we have a certain system has to do this. Try to break it down to small things, as small as possible, and then we make a PCB design out of it, and we order it, we assemble it, and then we see does it actually do what it should do, or is the circuit wrong, or should we change some things. And usually it takes 2 revisions to get a fully working PCB, and in our rocket there are like 15 to 20 PCBs, so it takes a lengthy amount of time. Oh, wow.
This is in the shot.
I was like, why are you watching? But,
keep going.
Really cool.
Okay, so you mentioned PCBs, I'm going to ask you what PCBs are, right? Okay, so that you can then edit it.
PCB stands for printed circuit board. So yeah, we make our circuits, and at some point we want to transfer them from the digital computer-aided design to the real world, and we basically give our circuit boards to a company, and they print them, kind of like paper, but then our circuits, such that we can work with them and actually assemble them. Yeah, so big companies with higher budgets, PCBs are relatively expensive to buy one and manufacture them, both time-wise and cost-wise. Big companies, they would just buy off-the-shelf stuff and just write code. However, yeah, we want to optimize for as much stuff as possible, and of course it's always fun to make your own things. So that's why we make all the PCBs in-house. We solder them ourselves, and we test them ourselves, and we write the code ourselves, so that we really have a product that's our own, but in the end it takes way more time to develop. For our development, our electronics relies on a lot of input from other teams, which a lot of the input, a lot of the information was only known later on in the process. So, for example, for recovery, they need to open the chutes, but the sequence on how they open it is undefined. So that led to that in the middle of the design process, we had to redo a board because we had to add a channel to the recovery PCB.
So what makes your team most different compared to other teams that work on Stratos IV?
Yeah, so this is a big debate in our team. We don't really do big test campaigns, or we may machine big parts or whatever. We make our stuff, and we test it continuously. We test the different parts of the and also if there's a piece of software wrong, we can just fix it in no time. It's not one big part. We verify with like 5 tests and it's done. For us it's more of a continuous integration. It's never finished. It could always be better, and that's a big difference. So we could end up writing code till the day to launch. So for other departments, they usually make a tank or a combustion chamber, like a big part. They do some testing campaigns on it, and they have an iteration. And for electronics, of course, there's a big hardware part, but also software part. And also the hardware part it's relatively easy to change or to test things. If a certain circuit doesn't work, you can kind of tweak it or change it while it's still in your hands. And for other teams, that's not so easy. So they do their tests to validate their stuff, and we basically continuously develop until we find a solution that's good.
All right, we just had a video about the electronics, but also a very exciting update you might have heard. We are now starting checklist Delta, which brings us to the point where we start to make sure that the engine is ready to be fired. So we'll attach the igniter, check the ground electronics needed for launch, and after this, the engine is ready and we can begin filling. So it's a really exciting update. And the countdown timer, as you can see, has also started, so we are good. However, now we move on to our next system, which is recovery. Niels, take it away.
So, as we mentioned before a few times, at Apogee, we separate the nose cone, and this piece we actually want to recover. So, there's a few reasons why we actually want to recover the nose cone. Mainly, it is that, first of all, as I just mentioned before we talked about the electronics, is that we have some payloads on board, and those payloads have some data which we really want to recover for the client. But furthermore, we also store our own data in some black boxes which are kept in the nose cone, which also have a lot of data, all the beautiful camera footage from our cameras, which are also placed in the recovery bay, etc. So we also, and all the acceleration data, the rotation data, all of this is really nice for post-analysis. And that's why we want to actually recover the capsule. So, to actually be able to recover the capsule, something needs to happen after we separate. Otherwise, it's just going to crash into the ocean and we'll never find it there. So, to actually land safely, you first need to be able to slow down the capsule. So, this happens in two main steps with two sets of parachutes. The first parachute is actually our drogue parachute. So, the parachute, its main aim is to make sure that our nose cone, which is tumbling down and then at some point makes a dive, which is going at supersonic speeds, then we actually get this back to speeds below the speed of sound. So that we do a massive slowdown with a small parachute that actually can handle it. This parachute is made with Tralon and Technoa, and it will be deployed by a HGGD, hot gas deployment device. So what this thing does is basically a small explosion that pushes out the lid for canister, and it pushes out the drum. But actually, before this happened, I kind of forgot to mention. When they're going down before the drug deploys, there's also a heat shield that we have. So this heat shield is a layer of carbon fiber with some cold on it that kind of makes sure that we don't burn any of our liners, which would otherwise be in open air and can't really handle the heat so much. So first we shield off the heat shield, and that's when the drogue parachute deploys. Then the drogue parachute, as I just mentioned, slows us down to below the speed of sound, but still it's not big enough to actually slow us down all the way for a nice impact. And that's where the second set of parachutes comes into play, and that is the main parachute. So the main parachute has a small pilot parachute which kind of reefs out the main parachute that then expands. The main is made with nylon, and it's actually deployed by a big compressed spring in its canister. And then when this main parachute slows it down to a lower altitude, that it actually, when it impacts with the water, it doesn't disintegrate, but it actually makes a nice soft landing. and then we can actually start to retrieve the nose cone. So how does that go into work? So as I just mentioned, on the main parachute we also have 3 live lights, which basically once they make impact with the water, they turn and they will actually start flickering lights. Furthermore, we also have some dye canisters in the recovery bay, which once they hit the water, some ultraviolet dye comes out towards the ocean. It's all made of biodegradable materials, so it's completely safe for the sea life. So that kind of spreads out, which helps us locate it. It's also, as you might have noticed, colored bright orange, which also really helps. But all of this doesn't really help if we can't even get kind of close to it, because all these are visual aids. So our last aid to actually find back and retrieve the nose cone is a beacon. This beacon will ping the location of the nose cone to everyone, so that we can kind of hone in on position, and once we get close, we have these passive measures to the back. So this is some things about the actual recovery system, but there's a video that we actually, before we go to the video, I would actually like to take a pause and give a shout out to one of our top sponsors, and this is Teijin. So as I already mentioned, our drogue parachute, it's made of an aramid material, trowel and technola. Furthermore, as I mentioned, our capsule, in the instruction bit I mentioned it, that the capsule is made of an aramid composite material, and all of these have been these materials are extremely strong and can handle the extreme thermal loads of the parachutes, both the parachutes and the nose cone during the flight. So this makes it also that the nose cone, the capsule, can have a safe way back to Earth. Teijin does not only help to bring Stratos back to Earth safely, but also helped in actually getting us to the pad in the first place, as they gave a lot of support in closing our budget gap and helped us fully fund the launch campaign. Furthermore, in previous years, our relationship with Teijin actually have given our recovery team the perfect opportunity to visit some of Teijin's actual R&D facilities and present its work to Teijin's technology at numerous conferences. We really look forward to the successful recovery and retrieval of the nose cone, and we would surely not have been able to do so without the support of Teijin. And that's why I would like to thank them on behalf of the Stratos IV team and there as a whole. And with this, I would like to also go to a video actually recorded by the recovery team itself, which explains all of this way better than I could ever do. So let's go to this video.
Welcome everyone. We had the opportunity to join the launch campaign of the Stratos IV rocket, where Sebastian is working on the recovery section of the rocket. He had a couple of minutes time to give us an idea of what the entry, descent and landing system of the Stratos rocket looks like. Welcome Sebastian, great to have you here. Could you give us an introduction of who you are and what Project Stratos is?
Yeah, so thanks for inviting me, Thomas. So my name is Sebastian Oliver Scholz. I'm currently the Chief Recovery of the Stratos IV project and a master's student at TU Delft. The Project Stratos is a project that started about 3 years ago, where we want to build a rocket fully done by students to reach and break the European altitude record, the student altitude record actually. And yeah, we want to do that by building a hybrid engine rocket.
Oh, very impressive.
Yeah.
So how does the recovery system specifically of the Stratos IV rocket work?
Yeah, so we use quite a few different systems for recovery. We first want to ensure that all of the internals of the recovery bay and the nose cone stay intact. So we use a heat shield to pretty much protect the internals during re-entry, during the heating phase. Then we deploy a drogue parachute. So we use a Hemosflow ribbon parachute for the drogue parachute. And then afterwards we deploy a main parachute after it's stabilized. And then this will pretty much slow the capsule down to about 70 kilometers per hour, and it will touch down in the sea.
Oh, great. So what kind of materials will we be using for the parachutes?
For the drogue parachute, we'll be using mostly aramid-based materials. So we use Triron for the canopy of the parachute, and we use Technora for the suspension lines and rudder lines. And then for the main parachute, we use mostly F111 nylon fabric for the canopy, and we use Spectra suspension lines, and also some nylon for the riser as well.
Good. All very high-strength materials, especially
Yes.
for the drogue.
Yes.
So you mentioned the drogue parachute, that it will slow down the capsule to velocities where the main parachute can be deployed.
Yeah.
But will you be deploying the drogue parachute at supersonic conditions?
For our case, no. The hemless ribbon parachute that I mentioned that we use for the drogue parachutes, it can be deployed supersonically, as a very wide range of Mach numbers that it can operate in, also dynamic pressures. But we saw that during our simulations that the nose cone is quite unstable during descent, and it will enter a flat spin, so it'll tumble. This will also bleed the velocity down a lot, which we saw that it would be more beneficial to deploy the drogue parachute subsonically, so at a much lower height. This will avoid certain flow phenomena that occur during supersonic and even transonic regimes.
That makes sense why use the high-risk scenario where you can keep it safe.
Exactly.
That makes sense. So what kind of deployment devices do you use to deploy the drogue and the main parachute?
For the drogue parachute, we use a mortar system, which we call the hot gas deployment device. It produces a very hot gas using nitrocellulose and some black powder for the igniters. We have a certain plenum volume that allows the the drogue parachute to deploy around 18 meters per second. This allows the drogue parachute to be deployed without being entangled, as the capsule will be doing a flat spin. And then the main parachute will be deploying using a very simplified spring system. This is because the drogue parachute will stabilize the vehicle, and therefore it will not be going down in a flat spin. And therefore we just went with a very simple spring system just to deploy the main parachute around maybe a few meters per second, maybe 1 or 2 meters per second, and just to keep it simple.
Oh, that makes sense. Do you use sort of a pilot chute for either the drogue or the main parachute, or do you just rely on the deployment devices themselves?
For the drogue, we don't use any pilot chutes. We attach the lid that pops out of the canister to the parachute bag. This will ensure that the momentum of the lid will take the parachute out of its bag. But for the main parachute, we use a fairly big pilot chute just for to ensure that the main parachute really gets out of its bag, and that's that.
Oh, interesting, very interesting. So what kind of testing methods have you used throughout the years to prove that these parachutes work, or prove that these deployment devices work?
Yeah. So for the mortar, we did a lot of different tests. We first tested using a battleship canister. This was just to test the proof of concept and see if it was actually feasible. We had very successful tests with those. Also to measure the internal pressure and the ejection velocity that we get by varying the amount of nylon bolts that we use for the lid. And for the main parachute, we did a tabletop test deployment where we just removed the parachute out of its bag by pulling it out of the canister, and we've also just had the whole system assembled and then just cut the wires using a pair of scissors and seeing how well that would eject the main parachute. And so far those tests were all successful. And not only that for the deployment systems, but for the parachutes themselves, we validated them in the wind tunnel by assessing their stability performance at subsonic conditions.
Oh, great that you can use a wind tunnel,
Yeah.
great resource.
Yeah.
So have you always used these types of parachutes for previous Stratos missions as well, or did they use different types of parachutes?
So for the previous Stratos mission, Stratos III, we used the same drogue parachute, so it's the same hemisphere ribbon design, same size and same shape, and we didn't see any need to change this design. But for the main parachute, we changed from a cross parachute for Stratos III to a disc cap band for Stratos IV. The biggest reasoning is because testing, the cross parachute is very unstable, and it was very hard to get any quantitative data from it. and we just saw that a disk gap band was a lot more stable, allows for a little bit better drag performance at a bit of a cost of volume, but we saw that was perfectly fine and we went for the disk gap band.
Great, yeah, the disk gap band is a beautiful parachute.
Yeah, it is.
Completely agree on that point. So how do you plan to find the rocket nose cone back after it has landed safely in the ocean?
Yeah, so for our final phase during flight, we have the retrieval module. From our simulation data, we saw that we will be quite away from the coast, so the nose cone will land quite far away. And therefore we use an Iridium module. So this is the active retrieval system. The Iridium module will give us an approximate location of where the nose cone is. And then we will navigate with the boat to the area where we have the location data and start a search pattern. And meanwhile, once we're in the vicinity of where the nose cone has landed, we will then look out for the passive system that we use on the nose cone, which is 3 strobe lights. So these are 3 water activated lights, which is mainly useful for night retrieval. And we also have fluorescent dye in water soluble bags that will also help us to locate the nose cone.
Oh, great to hear that you have multiple options to find this nose cone back.
Yeah.
Quite an endeavor. As a final question, also for the viewers, when will you be launching the Stratos IV rocket?
Yeah, so yeah, that's a good question. We'll be launching around the middle of October, so it's coming up very soon. So make sure to keep up on our DARE social media on Facebook, Instagram, and LinkedIn, because we will be live streaming it, and we definitely hope to see you there.
Great to hear. It's great to see that you're all working so dedicated on this project.
Yeah.
We as Shoots will be following carefully along with your launch campaign, and we'll be excited to see the launch. Thank you for spending the time with us, and good luck during the coming weeks.
Thank you.
So there we go, that video explained the recovery system way better than I ever could. So thanks for that. So next up, Liz.
Let's move on to simulations. Let's talk a bit about why it's important and quickly go over what we do. So, of course, when you're launching your rocket, it is important to simulate your flight because this helps you predict how the rocket will behave, how high it will go, when it will reach next point, and so on, how far downrange this can go, and so on. In engineering in general, whenever you have design, you're going to always supplement it with simulation and testing. And well, we can't always test launch a bunch of rockets to try to make sure that we are always landing in the right place and hitting the right altitude, so we simulate. So it is very important for safety, especially. We need to understand what kind of safety range we require for this rocket and for what apogee we require type of range. So this is all of these conditions of how high we can go is determined together with our simulations to make sure that we are always within the safe zone so that there is no risk to anyone else that is near us, right? So it is also important to understand when we need to terminate the flight or cut the engine such that the rocket still stays in the safety zone, because if you have an anomaly, which can happen, then you still have a worked out system for if you terminate it here or if you cut the engine here, then we know that the rocket will be safe and people on the ground will also be safe. So our simulations tool, our simulations team has developed an in-house tool for this. In order to do this, we simulate the trajectory with empirical data and think some Monte Carlo methods. We take as inputs the conditions, so we have the wind profiles and such, and all the conditions. And this is why you'll also always see us updating our simulations as we get weather data on the day of launch, right? So when we had data yesterday and we got updated data today, our simulations person has run these simulations again. We check them through with INTA, we make sure that it is okay and we are safe to launch. This is a very strong collaboration with INTA because they need to be confident in our simulations and we need to know that they trust us, and then we are sure that we can have a safe and proper launch. So yeah, that's an overview of simulation shortly.
Yep. And with simulations, we have actually mentioned all our technical teams, but that's not really where the launch campaign ends. I would also like to give a big shout out to all logistics teams. So as you just said, one part of the campaign is the rockets and the ground systems, but there's also an entire campaign around this. So people need food, we need housing, we need transport. And for all of this, we have our logistics team during the campaign. They are helping us with cleaning everything, with cooking food for us, and then also delivering us to the right spots at the right times. So we'd like to give a big thank you to the 3 guys who are kind of running all logistics for us. You guys are also invaluable to this campaign.
And I'd also like to mention that all of us help out with cooking and everything. So we have these head honchos who organize all this stuff, and we listen to them. But every day, you know, when we have dinner, different people are pulled in to help, and it's a group effort. And this is just one of the different types of aspects to a campaign that you might not think about as much. And next, I'd like to talk about PR and media. So, of course, money is needed for a campaign. So acquisitions is crucial for it. And we really owe a great amount to all our sponsors that have helped us here today, all the crowdfunders, all the organizations that have supported us. And also related to this acquisitions business is PR. So you want to promote yourself, you want to produce content that you can share with the world and with your sponsors. And this is a really big task. So we have a separate team working on all of this and has been working on this for the past 3 years to make sure that we can launch here today. You may not see them as much in front of the cameras, but they are everywhere behind the cameras. And really, we have many people in the campaign working on this as well right now. And looking at people, 3 people behind the screen right now, a few more in other adjoining. These are the people who make this live stream work, who make all our content, our posts on social media, the updates to the society and to the wider public. It's just an immense deal of work goes into all of this, and I'm really thankful for everything they do. We also have press keeping in contact with different newspapers and news outlets, making sure that we are ready to send out news about our progress and what we might achieve. Acquisitions is taking care of contacting our different sponsors and making sure that they receive updates about us as well, and that we are up to date with thanking them. And making sure that Stratos has the funds to break the barriers we hope to break. And yeah, as I mentioned, Livestream already, and PR just running around with cameras, taking pictures of everything. So really thankful to those guys. They are a huge, huge help in this campaign.
Okay, and with that, I would like to thank one more team that's doing your planning, so don't get concerned by me going off script a bit, but one that we forgot, and that is arguably the most important team of all, is actually management. We like to joke around here as the engineering team, like typical management always giving us stuff to do, etc., but they are actually the glue that holds all of us together. Right now, most of them are really busy in mission control. They've been doing all the planning for us, all the writing of the procedures, keeping the overview of the entire project. And honestly, without them like holding us together, making sure that we all interface correctly within the different departments, they, as I said before, they're the glue that holds us together. And without them, we wouldn't be here right now.
Absolutely.
Yeah. So with that, actually kind of rounds up all of our departments. So let's quickly go over the Stratos IV rocket. The Stratos IV is a 8-meter tall rocket. It is approximately 28 centimeters in diameter. It's a hybrid rocket which produces around 15 kilonewtons of thrust, and it has a 3D printed titanium nozzle. It has cold gas control wind control transistors. We have carbon fiber shells, tank combustion chamber fins. Our nose cone and parachutes are made of Trion, and we have a double deployment parachute system with a drogue parachute and a main parachute. And almost all electronics are developed in-house except for the flight terminating system, which is so critical that we went for a commercial off-the-shelf part. So,
let's talk a bit about, as a summary, also what this project really means to us, maybe personally as well, and to the team as a whole. So when we look back on the years that we've worked on this, what have we really learned? I think if I answer this personally, I can say that it has given me so much experience with actually working on a big project, having the chance to design, test, manufacture parts, and come to integrate launch campaign at the end, which is a really unique experience. It's taught me a lot about how to make design decisions, how to work in a team, just so much invaluable experience that you don't only get from your studies. So it's been truly invaluable. I think, Niels, what do you?
Yeah, so as Chief Structures, I've learned a lot about machining. That's like both carbon fiber composites, metals, lathe milling, all of that stuff. But besides that, also indeed working as a team, it's a real job, like managing people, making sure you interface with all people, having a lot of meetings, how to host them, how to make minutes, all of that is definitely a big thing that I've definitely learned over the past few years.
Yeah, you mentioned machining. I think I'm probably an expert in making radial holes at this point, because the engine is made up of a lot of rings with a lot of radial holes, and the amount of times I've done that is insane at this point. So yeah, very good point there. And I think for the future, Derek has also gained a huge deal of experience from this. From the whole Stratos project, really, it's been our biggest flagship for a while, and we've learned how to approach these big problems. Because with big rockets, you have big problems that require big solutions. And all of this comes together with the work of over 100 engineers, really, from people working full-time, people working part-time, lots of different departments. And I hope that this will help us in our projects going forward as well. For example, also Project Sparrow might have a lot to learn from a big-scale project like Stratos. Do you have anything to add here, Niels?
I think that's about it, but we also, besides the talkers, we also interviewed some other team members. So here's a little video of that interview. When working on this project, I developed a lot of manufacturing skills. This starts from metals, where I learned how to lathe and mill and do a bit of bench working with metals, to the other side of the spectrum, where I learned how to manufacture with carbon fiber composites.
And besides that, I learned how to work with pressure sensors. I learned how to work with feed systems and all the different type of feed system stuff that you have, because there are a lot of conventions.
The bachelor, you learn a lot of theoretical stuff and you do a lot of theoretical stuff, but not really hands-on a lot. You don't learn how to make a PCB or how to program one of the chips. So yeah, in there, all the boards are ours. We made them ourselves and we wrote the code ourselves. And I really have the feeling that I learned a lot making those.
So I think, doing the aerospace engineering bachelor at TU Delft, it's very intense. You know, you learn a lot of recipes in a sense of how to solve certain problems, design certain things, and you do also get opportunities to build them as well. Build, what you design in projects or whatever. But you don't get a lot of chances to not only design, come up with a concept, design, build it, and test it, but then also to now do another iteration after looking at your testing and making improvements. That's something really special that I think only dream teams or working can really offer you. So that's something that I learned in my DARE years very much.
I think the most important thing is that I learned to really look at the requirements and question them and to make things simpler. Because if you don't do that, then we really noticed how annoying it got and how much time it would cost us.
Yeah, I learned how to build an engine, how to manage the team, procedures. Also that before you have a test, you really have to set up your test goals correctly, because otherwise after the test you won't know if whether it's a success or not, and that will be a real issue.
Never trust electronics. No. Electronics doesn't work until it's been tested properly. That's a better way to phrase it. To illustrate this a little bit, I would say when someone asks me, do you have this finished? I can say, yes, I have the code written, yes, I have the hardware written, but I have not tested it, so it's not working and it's not finished yet.
The skills I developed most were the people skills. So being able to efficiently communicate with people and to really understand how people are feeling and how they think about certain topics. That really helps you to progress. What surprised me is how much people skills really influence the project. Most of the time when there are problems, they really arise from people not being able to communicate, or there being some miscommunication, or there might be some personal conflict on a personal level that then affects the project. and I did not expect that had such a big impact on the project overall.
So, of course, you join a team project. It's a team thing. Like, with just the electronics, you can't fly a rocket. But the people, like, aspect, how people look at it, especially when I'm an electrical engineer, and and most of the people in there are aerospace engineers. We really look at things differently. And yeah, for example, if a propulsion valve it opens, it might be really nice, but if it's electronically not properly hooked up and it's not sustainable, then maybe for the propulsion person it's perfect because it works, but for us it's garbage because it can't sustain it. And really those, I guess, different views on reality, on the same thing, is really what I was surprised by. Like, people look at things from what they know, and yeah, of course people know different stuff, but it's up to such an extent that I didn't expect it.
I think my biggest surprise was what for me at least is right now the definition of management and being a team leader. Maybe that was just because I had the wrong idea of it, maybe not, I don't know, but for me I was really surprised to find out that basically what it means right now to me being a team leader and managing is just enabling people to do their stuff. So not leading and directing and saying, okay, we're going to do this, la da da da, but checking with the team, okay, what does the team want to do? So that includes you, but it is everybody. And then from that moment, the only thing really is making sure that they will get there eventually, or they will have a chance of getting there eventually. But you want to make sure that they get there when you all as a team want to get there, so that you do it in time, you do it within money, within your constraints, that you don't need an given enough time or given enough money scenario, but given what you have, that you can get there, and that you also get where you intended to go from the start, or as you grow more as a team, realize where you really want to intend to go to. So being the helpful hand in all that, and because when you bring it down to the core, it's not the management and then later on you get other team members, it's the people who do the stuff, and then the bigger you get, the more management you get around it. So you're really, you're in a way enabling everybody. So in any like classical pyramid of like who's on top, the management is at the bottom. They're supporting everybody else so that everybody else can do what they really want to do.
Alright, welcome back after this video. Maybe to kind of close up on some of the learnings and experiences we've had here as well. Just being here at Intesadea in Spain is quite an experience, right? I think it's, we launched smaller rockets in there, and a lot of us haven't had experience with that, but doing something of this scale, a proper full launch campaign, is something that teaches you so much more about discipline and working with people, and just really stress test some of the relations that you have in your team. But it's been so much fun, and I've really enjoyed it. It feels like we're doing a really proper, very organized and very safe operation that just feels very nice to be a part of. What do you think, Niels?
Yeah, that sounds about right. Like our procedures, that book we have of about 80 pages of all checklists, just going through that, and has been such a difficult task to set up, but now it's really paying off, and you really can see how nice and neat procedures guide us through this launch day.
Yeah.
So with that, I would like to again answer some questions that have been popping up in the chat. So there is a question asking about how we measure altitude and what kind of sensors we use. So internally of the rocket, we both have our pressure sensors, which mainly work for recovery loads, for the parachutes when they deploy, at what pressure, etc. And then we also have some IMUs, inertial measurement units of board, who also give some signals about how we're rolling, and to control that with a active roll control system. And then furthermore, we also have a radar which actually is tracking the rocket when we go up. So we also have some external validation of our altitudes.
Yeah, exactly. Some other questions we got was relating to the goal of this launch, and questions about the altitude target and apogee we could be hoping to reach. So as Niels talked about before, the overall goal of the project is to really democratize space and show what we can do as students. And this definitely ties into the goal of the rocket as well. But maybe to word the specific goal of the rocket, we are trying to take back home the record for European student rocketry, the altitude record that is. And we are capped, as I mentioned, in our burn time and thus in our apogee as well by our capabilities with respect to launch sites. But we are hoping to tonight break the record, which is currently at 32.3 kilometers.
Yeah, that's right. So with that, I think it is time for us to go into a bit of a longer break this time. As you can see, the countdown timer has started, but we're still a while away from launching. So what we are currently going to do is, first of all, we're going to show a recording from Friday's live stream in which we actually interviewed two of the people that were at the Stratos III launch campaign. So it's a bit of an interview about how things were then related to now. So that's a nice view. So we're going to play that. And afterwards, the two of us are going to go a little break. And we plan to be back at you at 7:45 our time. So down here in the bottom right, you can see which time that is if you're on a different time zone. It's UTC+2. So at UTC+2, 7:45, we will be back at you with this hosted live stream.
Exactly. And before we leave, once again, I'd like to give a quick shout out to everyone that contributed to our crowdfunding and remind everyone that there is a link in the description if you wish to support Project Stratos and other projects in there further. And if you have any questions at all, we love to answer them. We like talking about our rockets, so throw them all in the chat. They are being gathered by our moderators, and we will check them as they pile up. Thank you guys, and see you soon.
See you.
All right, welcome back. That was quite a nice video we had there of the Stratos III launch and its aftermath. We have a very special interview lined up for you next. So this is a call with two special people. This is Stein Kohler, the chief engineer of Stratos III, and Deacon Foltz, who was the chief structures for Stratos III as well. So Stein and Deacon, can you hear us both?
Yes, you guys can hear us? No,
perfect. Then shall you both introduce yourselves quickly?
Yeah. Let's say Stein, introduce yourself. So as you can see, there is some technical difficulties with recording that interview from last week. So sadly, we won't be able to show it, and we're just going to go to the break, as I said before. So we'll be back to you in 45 minutes from now. See you.
Bye.
Do we know that audio?
All right, I think there was a problem with audio. I'd like to welcome everyone back to the Stratos IV launch show. This is Niels, I'm Liz, and we're here taking you through the launch of Stratos IV. Let's give you a quick update on procedures and where we are with launching today.
Yeah, so the update is that currently we have at the moment finished checklist Delta. This was the insertion of pyrotechnics into the rocket. So the rocket is at the moment completely ready for filling. This is also what currently we have given the go for filling from all the stations. So everyone is okay for filling the tank in the current window. So that's also what we have just about to split. Sadly, there's some bad news as well, that at the current moment in time, we sadly have a no-go for the weather. However, this is the weather we're talking about, and this could potentially still change. So that's why currently we go for filling. We're going to fill up the tanks, heat up the tanks to pressurize it, and then at a later moment we will deploy another weather balloon, so we can double check the weather situation to see if maybe it has changed in favor. That's why currently we are no-go for weather, but this could potentially still change.
And we are still, as Niels also already said, we are continuing with filling and after that pressurizing as well. And after that, for all intents and purposes, we can wait for the weather to get better within our launch window, which we still have hours left of, and then hopefully go for our launch tonight. So still very exciting times. This is not a no-go completely for tonight's launch window. This is just a current no-go for the weather. And we track this, as Niels mentioned, very properly with weather balloons. So we'll make sure to keep you up to date on whether we do have a go later. All right, so now that we're back from a slightly longer break, let's continue with some of the content that we have lined up. And let's start talking a bit more about DARE, Delft Aerospace Rocket Engineering, which we're a part of. Niels, take it away.
Yeah, so let's do a brief introduction of what DARE is. I already had one way early in the stream, but for the new people joining, I would like to repeat this one. So DARE is a society of rocket enthusiasts from the Technical University of Delft. So basically, in our studies, we all get all the practical stuff about how rockets work, etc. But some of us really feel the urge for some practical hands-on work. Our society has over 200 active members at the moment, and we all want to give young engineers the opportunity to be real rocket engineers. So we have numerous projects, teams, committees, all working on rockets, specific parts of rockets like nozzles, like parachutes, and anything else that you can think of that relates to rocketry. So we have rockets of various sizes, with rockets like Stratos IV, which are big flagship projects. We also have loads of smaller teams and smaller rockets, which are lowest time scale and money-wise smaller projects.
All right, so going over some of the history of DARE as a society. So in 2001, our history began, but then we weren't a society yet. We're a committee of a larger society that was composed of aerospace engineering students. And since 2010, we are our own society that is fully devoted to rocketry. We have multiple different workspaces, and we've had multiple different workspaces throughout the years. We've seen different projects and teams start up and end. But the spirit of student rocketry has carried on all throughout that time. In DARE, we have a lot of freedom to research things that you are interested in, that you want to do. That's why we have a fairly large turnover of different interesting projects that can end and start in a year even. And over these years, we've launched over 180 rockets from varying apogees from 1 kilometer up to 20.5 kilometers, which is our record-breaking Stratos II Plus rocket. So yeah, this is not only down to our members and the capabilities of them, but of course to our many supporters as well. And one of the biggest ones I'd like to highlight here is TU Delft. So besides being the university where most of the students who are part of their study, TU Delft is also the largest sponsor of the Stratos IV rocket. Whether it's been the facilities for our team to use, securing funding for launch, or helping us figure out any problems we might have, TU Delft has really been instrumental for the Stratos IV team and also for DARE. We would like to thank the Aerospace, EWI, and 3ME faculties in particular for their continued support over the years, in addition to Dean Henry Verhey and Professors Chris Verhoeven, Barry Zandbergen, and Eberhard Gill. Our team is looking forward to bringing the record back home to the TU Delft with the launch of Stratos IV. Thank you so much, TU Delft.
Thank you. And with that, we would actually like to move on to talking a bit about what we call our honorary members. So within our society, there's a lot of members, but there's also a select few people. So we would like to take the next 10 minutes to kind of put every single one of them in a bit of spotlight, show a bit who they are and why they're such a great help to our society.
Yeah, so starting off with Chris Verhoeven, who is an associate professor at TU Delft and has a PhD in electrical engineering from TU Delft as well. He is a project leader at the Delft Robotics Institute and has been a longtime friend and supporter of DARE. He has helped us get one of our longtime workspaces at the TU Delft, has aided us in so many collaborations and projects, and has been a fantastic advisor throughout the years for most people who have been a part of a board of DARE, as have I. Chris has always been a phenomenal support and helping hand for any problems you might encounter. So thank you so much.
So next on the list is Edwin Vermeulen. Edwin Vermeulen is the CEO of Aerospace Propulsion Products. He has been a long-time supporter for DARE and has worked in the aerospace industry for like over 20 years. APP is part of HyEnD Group. They make igniters for rockets such as the Vega rocket. APP has also supported over the years, and we're very thankful for that. Furthermore, Edwin himself has enabled some flagship projects to continue to excel and innovate, and especially for Project Sparrow, he has given a lot of feedback as he's very knowledgeable about the development of a liquid engine.
Next up, we have Barry Zwergen. Barry is a lecturer at the Faculty of Space Engineering at TU Delft as well. He's a long-time friend of us and is often seen at our many design reviews, helping pick out any errors we might be making, some exciting challenges that he may see in our problems and so on. It's really quite nice. He's really valuable for his knowledge in space engineering and his continued support and interest in DARE as well. As anyone in DARE can tell you, if you meet Barry in the corridors, you can always stop and have a chat with him. He's immensely interested in what we do, and we're really thankful for his interest and support over the years.
So next we would like to thank Henry Wehren. Henry is the Dean of the Faculty of Aerospace Engineering. So he has been a great support from the TU's point of view, specifically the aerospace faculty, as he has helped DARE to grow a lot. His support after especially the Stratos III anomaly, he was one of the first people to call the team leader back then up to ask how we were doing, how it was going. And also he has been helping us from workspaces to insurances and given us ample opportunities for promoting our work at events and such things.
Yeah, and last but certainly not least, it's Eberhard Gill. He is another professor at the TU Delft and the chairholder of the space engineering track at aerospace engineering as well. He's a very knowledgeable aerospace engineer, specifically in systems engineering, I would say. And he is another one of the people you often see at our design reviews, sharing his knowledge and supporting DARE and lots of other aspects. He's been instrumental for helping the launch of Stratos IV as some of our last critical reviews he was present at and giving really good feedback, as well as helping us get the documents required to get to this launch today. So we're really thankful for him and also thankful for all of the other honorary members we mentioned before. All right, so moving on, as Niels already mentioned, there is a collection of many projects and different teams. So let's just have a quick overview of some of them. We already talked about some, but we'll tell you about a few others.
Yeah, so the one I would actually like to start with is what we call SRP in our society. This is the Small Rocket Project. So this project is actually the most common inflow for members of our society. So this is an annual project that we host every year for first year bachelor students. So what happens is in this project we will group people together in teams of 6, and they get basically what we call the SRP engine, and they build a rocket around it, and their aim is to take an egg that they put in their recovery system. We shoot it up to about 100 kilometers, and then their job is to make sure that the egg gets retrieved in whole. So no scrambled eggs, no omelets, but a nice unbroken egg. So this competition, as I said, happens every year on all launch sites in the Netherlands. So they go there with their groups, and then to give a bit of an impression how this happens, we would like to show you the after movie of 2019 of the SRP project.
Alright, welcome back. We just saw the after movie of the Small Rocket Project of 2019, and so going ahead with some of the other teams in there, let's talk a bit about Sparrow. I already talked about this before, but for those who are newly joining us, let's go over this again. So when Stratos IV was planning for, a launch already, this was kind of the project drawing to a close, at least within the next year. And so last year, Dare was at a point where there were numerous members who were interested in starting a new large-scale project, working full-time on a project. And we've been building hybrids for years now with the Stratos project, and as most of Dare's other engines are solids, we have pretty much a lot of experience in both of these. But we haven't, although we've done some development into cryogenic engines, we haven't achieved a successful hot fire with them yet. So this group of people thought, hey, maybe we can actually build a larger scale liquid engine for Dare and fire this in a year as well. So they set the goal for last year to fire a thrust vector controlled liquid engine, and they achieved a successful 2-second fire in August in a battleship configuration. Congrats to the team, it was really quite an amazing sight to see. And the project is, of course, also continuing. So for the next year, the team has set a goal of having a full duration burn with this engine, and also not in a battleship configuration, but actually with the 3D printed very nice chamber that they have, which you saw in a picture here as well. It was quite amazing to see what a team could do in a year on such a complex system as a liquid rocket engine. And please check out our website for more info on Project Sparrow, and you'll see surely more info of them popping up as we continue this year with test campaigns and so on. Sparrow is a liquid biprop for anyone who's interested, with a Lux ethanol propellant combination, and we're really excited to see what they get up to next year. So I also have a video here to show you, which is the highlights from their last successful test campaign coming up right now. Yeah.
So that was a nice video of Sparrow's last test campaign, and again, we'd like to congratulate them with their successful ballistic fire. Then next I would like to continue on to our York team. So for those who don't know what York is a annual competition hosted in Portugal, in which loads of different rocket societies across Europe, they actually gather there to launch their rockets in this competition. So for this year, they went there for the first time ever in their history. And so we went there with a rocket which consisted of two 5 kilonewton solid motors. It was basically a Kenneth rocket, which we'll go into in a bit detail, but then a bit bigger. So it was mostly made out of sheet metal and aluminum. So they also had a payload, the Lunar Zero project, which is a student-developed ultralight lunar rover, which they wanted to, I believe, check some retrieval systems for. The rocket went to an apogee of 3 kilometers. We had a successful main parachute deployment, and I think we might have some footage of their launch. Then we'll just show us the video of that one. So there it is. So yeah, as you can see, the launches started off quite nice, but then
there was a minimal anomaly in flight. You might have noticed that as well. But as Niels already said, there was successful main parachute deployment. So that was still quite nice to see. And I think it was very special to see that the ignition was very nice, because these are two solid motors side by side in the rocket. So it was cool to see them igniting successfully like that. Congrats to the whole team. Really nice. Oh, we have a really nice picture of the recovery here as well. You can see it behind the plume. So congrats, Europe team. And I think it's really cool to look back and see that the air can really sustain 2 long campaigns at once, even on the same subcontinent, actually, here in Iberia. Right, so moving on, let's talk about Bloom. First of all, I'd like to say that global warming and pollution are, of course, an ever-growing issue in this world, and climate catastrophes such as floods and tsunamis are being impacted by this a lot. So we get more and more of these as this climate warming is happening. And the severity of these catastrophes can be helped by limiting soil erosion or by helping soil erosion in areas that are affected. And so this is where Bloom comes in. Bloom, as a whole, is a rocket that actually considers its impact on nature, which is not something that usually happens in rocketry. And its mission goal is to be CO2 negative over its whole mission. So Bloom has the goal of launching and dispersing soil erosion fixing seeds over an area. It's a simple, small rocket, and it is also made largely of biodegradable materials. So instead of having, say, an aluminium casing on your engine, you can make it out of plywood, and it works. And they've fired this engine and shown it as well, which is really quite cool to see. It's a simple rocket, so it's meant to be easy to build in areas where you might need to launch this kind of rocket to help save the soil erosion. So I think it's quite a future-forward project that really shows some of the innovative things that can come out of rocketry as well.
Yeah. So next I would like to move on to the CanSat project. For those who don't know, the CanSat competition is like a worldwide competition where students, old and young, they build like little satellites in, as you can guess, a soda can. So they have these contraptions, and as the Netherlands also has a CanSat competition, we provide the launchers for this competition. So as you can see, these launchers, they have been built in there a lot. So every year for the competition, we shoot 2 of these rockets into the air for the Dutch CanSat competition. We have a lot of iteration in this rocket, and this is one of the most developed rockets within there, as we are currently in version 7 with version 8 starting development. So yeah, that's it for CanSat.
Yeah, and last I'd like to talk about Spear. So Spear is a research project, and this is not a rocket project, but more of a research payload project, which is on board of another rocket, and that is the ESA project of Rexus Bexus. This is a project for students to launch experiments on board of a rocket or balloon, and we are launching on board of the Rexus rocket. So Stratos Spear 1 is the project that aims to test the Stratos stroke parachute at supersonic conditions. So unfortunately, the Rexus launch has been delayed due to COVID, and thus also the launch of the Spear 1 project. But to quickly talk about it, as I said, it aims to test the Stratos IV stroke parachute, which hopefully would have been done a bit before this campaign, but now is happening a bit after. It will land on land instead of water in comparison to Stratos IV, so it also lands on 2 main parachutes, which are pretty much similar to the Stratos IV ones, just slightly smaller, and there are 2 of them. And it's a research project, so it measures a lot more data than the Stratos IV rocket itself, so it measures the loads and all the forces acting on the parachute and such for research purposes. However, we are also starting the next Spear project, Spear 2, which aims to launch then on the next Rexus rocket. And this has the goal of testing a big main parachute and reefing mechanism for this parachute as well. So right now with Stratos, we separate the rocket from the nose cone and we recover the nose cone. But in the future, we might be able to recover the tank section as well with the use of a big parachute that is reefed. So this is quite a cool project for the future and shows what we might be able to do then. Both Spears are R&D missions as well. All right, then quickly, again, once more, I'd like to thank everyone that donated so far to the crowdfunding campaign that we had in spring. Really, your help has brought us all here. And remind everyone that there is a donation link in the description if you wish to support some of these projects that I've talked about. If any of these interest you, feel free to reach out for more information, sponsorship, whatnot. We are always very happy to talk and very, very grateful for the support that you guys give us. So, moving on, I think we saw a bit of a question in the comments asking about the different... So let's talk a bit about different stations in this whole launch campaign.
Yeah, so for this launch campaign, there is different people working at different places. You have seen some of them cycle by on the live stream, some of them are not on the live stream. So we'd like to just take a moment to go across all of them. And I think there's no better place to start this talk than with mission control. So mission control is the central room where together, I think, 6-7 of our people together with the personnel from INTA, they're sitting there and they are having the big overview of everything that's going on. Here you can see them. So in this room we have our test conductor who has all the procedures in front of him. He kind of, together with people, plans things. They keep checks on all the rocket statuses, how they still go for launch, those kind of things. They are the ones that actually lead this operation.
We have the chief engineers there who know everything about the rocket and the mission and are also there to make sure that everything is going well. Our team manager is sitting there keeping an eye on everything and how it's going. We have our simulations department there working, continually running simulations as we get more wind data and making sure that we are safe to launch. Yes, I'm forgetting anyone?
We're forgetting Ofcom, the one who kind of keeps in touch with the less critical stations within the launch, which we will go over in a bit. But I think we're first going to go over like the main loop, the main people doing stuff. So I think with that one we can move on to our next station, which is the bunker. Here in the bunker, this currently also has our pad crew in it, so I think it's better to just combine those two right now.
So obviously you saw people working on the pad before and people working in the bunker. But now once we are on to checklist Echo, then we are clearing the pad because no one is going to be on there while we're filling and heating the tank, just for safety reasons. And so they have now gathered all in the bunker.
Yeah, so the pad crew mostly consisted of some of our propulsion engineers. Yeah. It consisted of our PADS conductor, who is basically the one who is in direct communication with the conductor in mission control. So them two are the main two people talking to each other and conducting the operation. Then they also have a safety officer there and some of INTA safety officer. So that is the pad crew. And then for the bunker crew?
Yeah, we have people in the bunker and these people will make sure that we have the controls of the rocket there and we are also logging data on there. We have a telemetry feed to the rocket from there, as we'll talk about some of our other telemetry stations as well. and these people will be staying there in the bunker, which is a few hundred meters from the pad as well.
So I think the next station, shall we talk about this?
Yes, we can talk about us.
Yeah, we are the live stream. As you know, you've seen us the entire latter half of the day. So we're hosting a live stream. Behind us are the people also running the internal live stream with all the views for between mission control and the pad, so that they know what is actually going on.
And we have some PR and press people in different rooms of this building as well. A few buildings over is the media room. See a lot of the engineers who have worked on this rocket just watching the streams as well and seeing what's going on. Let's talk about maybe some of the external stations as well. So, most of us, the pad is some kilometers away from us, as is the bunker, but we're still sort of in this vicinity. But there are some further away stations.
Yeah, so I think the first one to talk about will be our Mata station. We can't really get a camera there because they don't have a camera with them, but I think they are about 20 kilometers away from us. Might be slightly off that number, but they are there with a really big antenna. So what they do, like we have close by telemetry station on the bunker, but once we go like a few kilometers in the air, that station on the bunker won't be able to track the rocket anymore. So at that point, we have our big dish way far in the distance who manually track the rocket into the air so we can still receive telemetry even though a close by telemetry station doesn't get it anymore.
Yeah, that's correct. So there's a few people sitting there with a big dish pointing it at the sky. They'll soon be under the stars. It's quite an experience probably to see the rocket launch from a completely different angle. And aside from Mata, Intel also has 2 telemetry stations. So we, as Nick mentioned, we have one at the bunker that is pointed right at the rocket as it's taking off. And then we have 2 inter-telemetry stations and one of our own telemetry stations that we call Mata, which are all tracking the rocket and receiving data from it as well. And last but not least is the boat.
Yeah, the boat. So as we mentioned before in this live stream, the nose cone, the capsule, we actually aim to retrieve it, to recover it. So currently there is 3 people standing by in the harbor in the town next door. There's a big harbor. They're standing by boats, waiting for our go sign that we are go for launch. And once they get that sign, they start sailing to the edge of the safety zone. And then once we've confirmed splashdown, they actually start the retrieval operation and start to look for the nose cone.
Yeah, and that's also quite an interesting point to be at because it takes, I think, an hour or 2 to sail out from the port into to the edge of where we expect to land. Then once the rocket has launched, you start receiving some beacon pings from it, which brings you closer to the region you're in, but that is still could be a 2-kilometer radius to search with a boat in the night. So it's quite an exciting job. They might be up for a fair bit longer than most of us tonight as they try to find the nose cone in the waters.
Yep, that's true. I think with that we've kind of mentioned all our stations.
I think that's correct. And I think it makes sense to take a quick break here as well. Remind everyone that Q&A is still very open, so feel free to ask anything that you might be interested in, and we'll try answering it later as best as we can. And we'll see you back here in 5 to 10 minutes.
Yeah. Welcome back, everyone, to the Stratos IV launch live stream. This is Liz, and my name is Niels, and we're back after a break.
So we have another update for you. So while we were starting filling, we detected some minor leaks in the system. So we are ready for this. We have procedures for this. We are proceeding with checklist Zulu, which means that we will be dumping the small amount of nitrous that we have in the tank right now. Then we will cycle the valves, and we will continue filling again to check if this was just a small anomaly.
Yeah, and with that, we'd like to go back to the show we have prepared for you guys, and we'd like to start talking a bit about the history of Project Stratos now. So basically, this starts over 10 years ago, when there was still a young society, and we first started dreaming bigger than we were at the time. So at the time, this is back in the 2000s. The project started, and our aim was to break the European amateur rocket altitudes record. So we did this by starting the project Stratos with the Stratos I. Stratos I was a two-stage rocket, where first we had the first stage, which consisted of 4 solid boosters with 1.5 kilonewtons of thrust each, and a further one. After that propelled the rocket to Mach 1, we had a second stage, which is the Stratos Sustain, which propelled the rocket to Mach 3. So this rocket actually launched in Sweden in 2009, and it had a separation system where it shed off the boosters, and then the main sustainer with the nose cone attached to it was actually planned to be recovered. This rocket actually managed to reach an apogee of 12.5 kilometers, which at the time did give us the altitude record for amateur rocketry in Europe. So that was a great step for there, where we got our first record. So the boosters were not intended to be recovered, and the top section it had a downlink with telemetry. However, after separation, we did not immediately find back the sustainer. So 1 year later, a rescue mission was actually set up where some people went to actually look for it, and they did actually manage to find it in the end. So we found the wreckage of the Stratos I. So at that point, the project had come full circle.
Yeah, of course. And then after Stratos I, there was Stratos II. So first of all, I'd like to give a shout out to some of the sponsors that we've had with us since that time already. So first of all is HyEnD Group. And I'd like to say that having 31 nationalities, I think, represented within the Stratos IV team over the years means that working with people from different backgrounds is a core part of who we are. This mentality is also really prevalent in our sponsor, HyEnD Group, which embodies that same spirit of international collaboration which we strive for in our team. After sponsoring Stratos II+, Stratos III, and now also Stratos IV, HyEnD Group has been consistently dedicated to our mission to democratize space over the years, and even through tough times during the pandemic has supported us. They've stuck by our side, which has really enabled us to continue our ambition in breaking boundaries and showing the work we students can be capable of. Being the developer of the HyEnD rockets, they are also the type of company that most of us would really love to work at one day. So we are really proud to call HyEnD largest sponsors of the Stratos IV project, and are extremely grateful for their continued support.
To move along on that message, I would also like to thank Stud. So Stud, after having sponsored both Stratos II+ and Stratos III, Stud decided to once again sponsor us for Stratos IV by actually purchasing a flight termination receiver. The flight termination receiver is a very important part of our flight termination system. And without their support, we actually make our launch way safer. So Stud also enabled us to fully fund a launch campaign here at INTA, to which we are internally grateful. Besides Stud helping fund students, projects, and initiatives around the campus, Stud also provides amazing opportunities for students to find work alongside their studies. A big thank you from the Stratos IV team and there as a whole for their support.
I'd also like to, just in case anyone doesn't know, we have the radio loop right here in our ears. That's why when we update you about procedures, we can hear them working right now. They are completing their procedures. So we'll keep you up to date if there's any significant updates in that as well. But then, to continue, I'll tell you more about Stratos II and Stratos II Plus as well. So, Stratos II set out the mission goal to launch a rocket to 50 kilometers altitude, carrying on board a scientific payload designed, built, and manufactured by students. This was attempted to launch in 2014. Unfortunately, there was a misfire due to a leak in the oxidizer feed system, which led to the main valve between the oxidizer tank and the combustion chamber freezing up. So there was a successful ignition, but there was no engine fire. So over the course of the next year, many of the systems of the rocket were designed again and redesigned to be better, and more tests were performed on them as well. And next year, the team came back with a new rocket that was now named Stratos II Plus. It was designed to fly up to break the student European altitude record, carrying a scientific payload and to be recovered after launch as well. The subsystems were developed and designed in-house, making Stratos II Plus one of the most technically advanced student projects at the TU Delft. It combined high-power experimental propulsion, sub- and supersonic aerodynamics, advanced safety systems, telecommunication, supersonic re-entry, you name it, and also, of course, international collaboration with a huge team. So, Stratos II was also the first rocket to be launched here at Inta and we're really thankful for their support and really happy to be back here now as well. In total, the Stratos II Plus had a length of 6.9 meters, with most of its length taken by its single-stage hybrid rocket engine. This engine was developed by Dare and known as the DHX-200 Aurora, and this engine is actually the precursor to the Nimbus engine today, which is essentially just a sized-up version of the Aurora engine. It had a total impulse of 180 kilonewtons per second and a total burn time of around 23 seconds. So this is compared to the nominal burn time of 38 on the Nimbus, or 28 as we're capping it today. In total, 14 static tests at TNO and DLR facilities were performed. So this is a very tested and verified engine as well. It had a dual parachute system in the capsule section of the rocket with one throw chute and also a main chute. The nose cone included the flight computer, power and data management systems, downlinks, and also a commercial payload. And the flight computer and telemetry were also developed in-house and measured tank and combustion chamber pressure, accelerations, atmospheric pressure, the orientation of the Earth's magnetic field, and the power being consumed by the different subsystems of the rocket. It was launched in 2015 from El Arenocio here at Inta and reached an apogee of 21.5 kilometers, which meant that we brought the record home again by setting another altitude record by Stratos and Dare for European student rocketry. So, moving on.
Yeah, so after sponsoring the record-breaking launch of the Stratos II Plus in 2015, Flow Traders once again sponsored the Stratos IV at the beginning of our project. Their assistance has enabled us to develop early iterations of some of our subsystems for testing. The Stratos IV team especially enjoyed the interaction we had between Flow Traders and our students, as we hosted events both at Flow Traders and at our place. So, before the pandemic, these were really exciting for both sides to get to know each other and to see what the other does. Some of the students even went to do an internship at the company. So we would like to thank Flow Traders extensively for their confidence in us and their support.
Yeah, and for another sponsor shout out, let's talk about Airbus. So being one of the most familiar names in the aerospace industry for most of us, and so our largest sponsor is the Stratos IV, Airbus Defence and Space deserves a massive thank you for their support of our project. It goes without saying how important it is to have continuous support from project to project to really continue the development and innovation over the years. And Airbus Defence and Space is really the embodiment of that and has supported us as Stratos with every rocket since our last record-breaking rocket, which was Stratos II Plus. So Airbus Defence and Space is extremely active in the space industry, and many of our students have been able to meet and speak with their employees at various events, which has been a really nice experience and created a really nice atmosphere for students to talk with some of the top contributors in the industry. It goes without saying that for most of us, we would love to also work in a place like Airbus one day, and really want to put our feet in the right direction with another record-breaking launch. Thank you, Airbus.
So yeah, we left off at Stratos II, where we as Dare broke the altitude record. However, in 2016, this altitude record set by Stratos II was broken by a German team from Stuttgart, where they reached the apogee of 32.3 kilometers. So, consequently, once they got the record, a team in there decided to set up the Stratos III. And the main mission of the Stratos III was to improve this European altitude record for student rocketry once again. So, the Stratos III, the baseline for this rocket was once again, like the Stratos II, was a single-stage hybrid motor with the DHX 400 Nimbus, which is basically the big brother of the Aurora as mentioned for Stratos II+. And it's the same engine we use in Stratos IV actually. So this engine has an average thrust of about 15 kilonewtons with a 20-25 kilonewton peak thrust, and it was designed for a burn time of 28 seconds. The Stratos III, kind of like the Stratos IV, was about 8 meters long, and it was a 330 kilogram wet mass vehicle. It's similar to us, had a nose cone which you would recover with a cold gas drogue parachute and a spring-aided main parachute. The Stratos III rocket was launched in 2018. However, this is where the story turns slightly less rosy. And 20 seconds into flight, we had an anomaly occur, and the rocket disintegrated at an altitude of approximately 10 kilometers. So, why did this happen is then the next question. We encountered a phenomenon that we call wall pitch coupling. We will explain this in a bit more detail in a moment, but let's first look at a launch video for Stratos III.
So that was the launch video from Stratos III, but we also have a after movie which might better capture some of the emotions and feelings around that launch. So let's show that right away as well.
Intel's ready. The systems are ready from our manager.
We have to go for the launch.
All right, Tango Charlie. We would like to hear your reasoning for why exactly you want to cycle the main.
Final countdown of the Stratos III sounding rocket. 5, 4, 3, 2, 1, 0. Yeah. We lost the vehicle. Over.
So hope you guys enjoyed that Stratos III after movie. As you saw, it had a kind of sad ending where the rocket broke up in the air and disassembled itself. What actually happened here is what is called roll pitch coupling. So basically, what happened during the launch is the rocket started to enter a roll. This roll then, as there was some sort of instability in the rocket, it started accelerating. So at the moment, this rolling rate hits the natural frequency of the rate it likes to make this motion. So what happens at that point is that energy between this roll and this movement is nicely transferred to one another, which means that as you start rolling, at some point you start making this motion. So you start getting this, that starts increasing, and at some point the rocket is sideways. And I don't know how much you know about rocket dynamics, but this is not the way a rocket is designed to go. So you had a aerodynamic breakup in the air, and that is why Stratos III met its end. So, of course, after the Stratos III launch, the first thing that we did as a society is we kind of started a investigation into what happened. Like, the outcome was this, but how did we get there? And for that, we have a nice video with two of our safety officers who are kind of talking about this phenomenon and the Stratos III investigation.
2, 1, 0.
Hello guys, so why don't we start off with a short introduction. Dion?
Yeah, I am Dion. I have been in DARE for I've been in DARE for 7 years. This is my 8th year. Yeah, I've studied aerospace engineering.
Okay. Rolf, what about you?
I'm Rolf. I am now in my 7th year at DARE. I'm studying aerospace engineering as well, as I suppose most of us here.
Okay. So over the past 3 years, we've had this project Stratos IV. What have your guys' roles been in that?
In the start, I was a full-time propulsion engineer, which means I helped out with developing the main engine, as well as Stratos III forensic investigation, and that sort of culminated into my role as roll control propulsion engineer.
Yeah, for me personally, I haven't been as involved in Stratos IV as Wolf has. I was briefly involved at the start, but then left the team because I didn't have the time to spend on it, and then I kind of moved on towards more safety roles, and I was doing basically being safety officer for all of the ladder tests that they did for the propulsion team, for example.
What does being a safety officer entail?
Right, so you can imagine that building rockets is kind of inherently very dangerous, and especially when you deal with stuff that's at super high pressure or using pyrotechnics, you want someone there to make sure that people aren't doing anything stupid necessarily. So I'm just kind of there to oversee what people are doing, make sure that they're not doing anything dumb, and yeah.
So both of you guys are involved in the Stratos IV launch campaign, which is why you guys are in Spain. So what are your guys' roles in the launch campaign?
Yeah, so kind of a continuation of what I was doing for Stratos for not really being in the team is that I will be the pad safety officer. So basically you can imagine that anything you do for an engine test, you're kind of hooking that all up to a rocket now. And you want to make sure that people that are doing stuff there or doing stuff with flight termination systems and such, that the people there are doing it, but they're doing it in a safe way, and no one's going to get hurt accidentally or anything. So that's kind of what I do for Stratos IV.
I think that really runs in parallel with what I'm doing as well. I think the two of us are in general responsible for safety of this project. My role is flight director. It sort of originated from the Stratos III investigation as well, knowing how the anomaly went, being involved with the chief simulations to develop some of the software, where I was advising on implementing safety aspects into that simulation, and that in the end culminated into being the flight director, so together with INTA personnel ensuring safe execution of the flight of Stratos IV.
Okay, so both of you guys were part of the Stratos III launch campaign. So what were your roles for that?
During the Stratos III launch campaign, I joined and helped building up the Livestream. I wasn't involved in the Stratos III project necessarily. I worked on some of the smaller projects in there, gained my experience. And here was a lot of watch and learn, see how a launch campaign is executed, and see how things are done.
Yeah. I was also involved in the live stream, although before going to the launch campaign I was already heavily involved in the propulsion team, which is also why I helped out the Stratos IV propulsion team a little bit when they started out, and also more towards the end. So I was there doing some stuff on assembling the engine, that sort of stuff. And then later, when all that stuff was done, then we basically just had to put the engine on the rocket. I was hosting the live stream, so I worked a lot with Rolf then. He did all the technical stuff. I just had to look pretty and talk to the camera like I'm doing now. Hello. Yeah, so that's kind of what I did during the Stratos III launch campaign.
Okay, so Dion, since you were a bit more involved in Stratos III, what was the aim of that project?
So the aim of Stratos III was to kind of go as high as we possibly could with what we had available to us. We had a lot of lessons learned from Stratos II+, which was the rocket that we launched before, and we kind of wanted to see like what we could do like with the means we had to go as high as possible. We learned during Stratos II+ it's a bit silly to set a specific altitude goal, because if you don't reach it, you look a little bit silly. So we just said like we want to go as high as possible, and that's kind of what we did. Well, you know, kind of what we aimed for at least.
So I can imagine that you guys had a lot of problems during your project. What kind of problems did come up, and how did you overcome these during Stratos III?
I mean, yeah, we certainly did. I mean, I obviously was very much involved in the engine development, and boy did we develop that engine. We did so many tests in the end, and we had so many failures because these engines, we basically built the biggest engine at the time ever built by students. And the type of engine we use, a hybrid rocket engine, doesn't necessarily scale very well. So it was double the size of what we used for Stratos II+. Completely new engine, and that means that manufacturing becomes difficult. You now have to lift an engine that's 100 kilos instead of like 25, 30. Like, it becomes a lot more difficult in that sense, and that's just from a propulsion point of view. It's just very, very high level. If you look at the electronics have been completely redone. We didn't really work as much with composites before this. The tank is immense. It was basically the big size constraint on the rocket, and like just, you know, the thing that set how high and how far we could go. So that there was so many different things. Also, flight termination systems, which had to be professional rather than us making some circuit board. We actually had to get it certified and such. So all of that was very, very challenging, and in the end we did overcome most of those challenges, and we eventually launched the rocket. So yeah.
So yeah, you guys launched the rocket. However, mid-flight a anomaly occurred. What was your guys' reaction to that?
Well, it was kind of a punch in the gut, to be honest.
Yeah, really.
Like, I mean, like, I had like some data streams open on my laptop as well, so there was no guesswork really involved to be like, okay, we lost the rocket. But man, it felt really bad. I mean, of course, for me, I was working on that rocket for two years or so already, and then all that work is just suddenly gone. And then the second thing I thought was, I hope it was not something that was directly my fault, because, you know, it's everyone that's worked on the project, and everyone's like kind of like, well, man, I'm not sure how to react to this. Like, I'm not sure what happened. No one knows what happened, and yeah.
Yeah, I remember when the rocket launched, the Livestream was switched over to this Optronics third view. So we looked in that case at the infrared footage of the rocket, and at some point there was this black blur around the rocket, these circles. I was like, oh, this does not look good. And then suddenly it was all in focus again. Turned out there was a lens switching. But basically 3 seconds after that initial relief, suddenly everything just stopped. You saw a bunch of black dots, and that was it. And then you realize this does not look good.
Yeah, plus everyone was absolutely exhausted because we launched this rocket at 3:30 in the morning, and at that point we had been heating for five and a half hours. And of course the entire day leading up to it. So everyone was really tired, and it was just really an awful feeling.
I think one thing that's really noteworthy though is that this team was able to launch the rocket at 3 o'clock at night.
Yeah.
It just shows the perseverance they had in order to push this through. There are some technical difficulties they had to overcome during that one launch attempt. And all the other launch windows that were open in the days after didn't have wind conditions that were favorable enough. So the fact that they managed to get that rocket to lift off on that one day is just an immense result.
So Rolf, earlier you mentioned that you were part of a forensic team that looked into what happened during the Stratos III anomaly. So what was your guys' thought process going into this investigation?
I suppose the first thought process was like, whoa, this system is complex. The problem is complex, the data is limited. How are we going to address this? We were with 6 engineers, mostly Stratos IV, which means we were continuing the project but not necessarily so involved in the Stratos III project. So there was a lot to learn about the rocket, about the vehicle, and just trying to tie all those theories together. All the theories that the experienced members had, the ideas of what could have gone wrong, and figuring that out was one of the largest challenges there. So after sorting out all the theories and ideas of what may have caused the failure of the rocket, we started collecting supporting and opposing evidence for all of those theories. Then some of them are rejected, otherwise stay open. And in the end, the one open one was inertial roll coupling of the rocket.
So another name for inertial roll coupling is also roll pitch coupling. What exactly is this phenomenon?
What it basically entails is that the rocket wants to spin at a certain rate, so it starts rolling on its axis, and then it stays at that rate, and it basically starts to make this cone motion. So the tip of the rocket starts to move around in circles, and that just becomes more and more excessive over time, and at one point the aerodynamic forces become so large that the fins shear off and the rocket breaks up. Well, one large important factor in roll pitch coupling is the structure of the rocket, so the stiffness of the entire assembly. If the rocket starts bending, your thrust will not go straight through the center of the rocket, so as you can imagine that helps pushing it to the side a little bit more. So that's one large factor. And there's other factors such as how symmetric the rocket is built, as well as slushing of the oxidizer.
Okay. And what was the method for preventing roll pitch coupling on the Stratos IV rocket?
So the method was twofold. One part was do as best as we can, but we can't quantify this. And the second one is we can quantify it and want to test it. The first one was improving the stiffness of the rocket and also improving the stability of the rocket. So you'll see the fins are a completely different shape as they were for Stratos III. The problem is that you can't quantify if that work is enough in order to battle this problem. Therefore we decided if you use a roll control system, it's a system you can test separately beforehand. You know how it performs, it's predictable, and that would make us more comfortable in knowing that this launch can be a success.
Alright, welcome back. That was a video that saw two of our safety officers discussing the Stratos III anomaly and some of the topics relating to that. So to sum up, this anomaly kind of leads into the motivation for Stratos IV as well. So we wanted to improve upon Stratos III and launch basically an improved and updated Stratos III that can now achieve its full apogee as well. And also to show that we can do this as students and thus democratize space in our own way. Show that we are capable of doing these things even with the resources that we have. So yeah, Stratos IV is based on the Stratos III with improvements made to counter roll pitch coupling, although there are also other improvements made in different parts of such as weight saving, we have a heat shield, there's numerous changes that we've discussed before as well, but the largest motivation for sure, I think, was the roll pitch coupling. So yeah, from here on, I think Niels.
Yeah, so before we leave you guys for another break, I would quickly like to once again thank all the people that have helped us in the crowdfunding past spring. With your support, we managed to raise a whopping 15,000 euros, and this has greatly helped us and actually enabled us here, because without that money, we wouldn't have been here today. So thank you everyone, and if someone wants to donate any future projects from there, there's a link down in the description where you can donate some money if you want to. And with that, I think we are going on a bit of a break. So we'll see you in about 15 minutes, I believe.
Yeah, see you then.
Live to copy.
All stations, this is Tango Charlie. I would like to hereby announce the final decision of a launch in this window. Due to leaks in the system, we are a no-go for launch today. We will now continue cleanup through the X-ray procedures. This will be led by Corso and Papa Sierra on pad. Tango Charlie out. File, this is Tango Charlie, please come in.
This is Vile, please go ahead.
As per step X-ray 1-3, can you please confirm that the flight computer is disarmed?
Jasper will take over comms.
Say again?
As per step X-ray 1-3, can you please confirm that the flight computer is disarmed?
Yes, I can confirm the flight computer is disarmed.
All right. Can you please confirm that all the other steps in X-ray 1 are not applicable to our situation and we'll continue at X-ray 2?
Yeah, I can confirm. We had the same thought and we were about to ask actually. So for us, we are good if we can start at X-ray 2. Over.
Copy that. Continuing at X-ray 2-1.
Alright, welcome back to the Stratos IV launch show. This is Niels, I'm Liz, and we have an unfortunate update to give you. Unfortunately, we are a no-go for launch tonight due to the pertaining issue we had with leaks in the system. We do not consider it safe enough to try to continue fixing these today, and we cannot go for a launch today. So we will continue by disarming the rocket and disassembling it as little as needed and completing cleanup for tonight.
Yeah, so tomorrow we'll look into the issue, we'll see what's wrong, we'll try to fix it, and then our next launch window is this Friday and or Saturday. We have both those days. We'll see which weatherways makes the most sense, and you'll be seeing us back again during that launch attempt. And for now, we'll see you then.
Thank you for watching, thank you for following along for everyone, and for your continued support. This is unfortunate and sad. We are also sad to see this, but we will be coming back in a few days, hopefully with all of these lost issues fully worked out.
See you on Friday.
See you.